everything you were taught about time, space, and reality might be wrong. What if time doesn't tick the same for everyone? What if the universe has no center, and most of it is invisible? What if reality only becomes real when you look at it? These aren't science fiction. They're the strange truths hidden beneath everything you thought you knew. Stay with me, because by the end of this video, your understanding of the universe will never be the same. Time isn't universal. Time. We often think of it as a steady, predictable river flowing from the past to the present and into the future. We set our clocks by it, plan our days around it, and live our entire lives according to its rhythm. But what if time isn't as simple as we've always believed? What if, instead of being universal, it bends, stretches, and slows, depending on where you are and how fast you're moving? This is the startling truth revealed by Einstein's theory of relativity, a truth that shattered the classical view of time and changed the way we understand the universe itself. Albert Einstein's theory of relativity tells us that time isn't an absolute backdrop against which events play out. Instead, time is intertwined with space itself, forming a flexible fabric called spacetime. According to this theory, massive objects like planets and stars can warp spacetime around them, and the faster you move through space, the more time slows down for you. It's a truth that sounds like science fiction, but it has been tested, verified, and woven into the technologies we use every day. Time, it turns out, is not the same for everyone. To truly understand this, we have to start by imagining a universe where space and time are not separate entities but are fused together. This idea, known as spacetime, is central to Einstein's theory. Just as you can move left, right, up, or down in space, you're also constantly moving through time. But the catch is this: how fast you move through space affects how fast you move through time. It's as if the more you rush through space, the more your progress through time slows down. This concept is called time dilation, and it has been proven again and again. Let's take a simple example, one that exists far above your head right now. High above Earth, GPS satellites orbit the planet at incredible speeds. They rely on extremely precise timing signals to help determine your exact location. But the clocks on these satellites don't tick at the same rate as those on Earth's surface. That's because they're moving quickly through space and are farther from Earth's gravitational field. Both of these factors, motion and gravity, cause time to move slightly differently for them than it does for us down here. If engineers didn't account for this discrepancy, GPS systems would quickly become inaccurate, drifting by kilometers each day. It's one thing to read that time slows down at high speeds, but another thing entirely to see it play out in real-world systems. GPS systems demonstrate this truth elegantly. If time were truly universal, if every clock in the universe ticked at the same steady pace, then the corrections needed for GPS would be unnecessary. But because Einstein was right, those corrections are essential. And while the time differences involved are tiny, measured in billionths of a second, they make all the difference in the world for pinpoint accuracy. Time dilation becomes even more extreme when you approach the speed of light. According to Einstein's equations, as you move faster and faster, time slows down more and more relative to a stationary observer. If you could travel near the speed of light, you would experience time far more slowly than someone left behind on Earth. For example, astronauts on a high-speed journey to a distant star might age only a few years, while decades could pass back home. This isn't just theoretical. Particles called muons, created by cosmic rays in Earth's upper atmosphere, decay more slowly when they're moving quickly. Without this time dilation effect, they would never reach the Earth's surface. But they do, just as Einstein predicted. Gravity, too, plays its part in the dance of time. According to general relativity, the stronger the gravitational field you're in, the slower time moves for you compared to someone farther from the source of gravity. This is why time moves ever so slightly slower for people living at sea level than it does for those at the top of a mountain. The difference is minuscule, fractions of a second over a lifetime, but measurable with today's sensitive atomic clocks. The warping of space-time caused by Earth's mass slows down time itself near the surface. Now imagine standing near the event horizon of a black hole. There, gravity is so intense that time for you would appear to almost stop relative to someone far away. From your perspective, everything might seem normal, but to an outside observer, your clock would tick slower and slower the closer you get to the black hole's edge. In fact, they would never see you actually cross the event horizon. You'd seem frozen in time. This isn't a trick of perception. It's a real physical effect caused by the curvature of space-time. In the presence of extreme gravity, time stretches like molasses. This understanding of time has transformed not only our view of the cosmos but also our practical technologies. Consider international timekeeping and satellite communications. The atomic clocks aboard satellites need to account for both their high speeds, special relativity, and their distance from Earth's gravity, general relativity. Engineers apply corrections to these clocks so that the time they report matches the time experienced on the ground. Without relativity, modern communication, navigation, and transportation would quickly spiral into chaos. The satellites would send inaccurate signals, and every time-stamped financial transaction or flight path would drift off course. But perhaps the most haunting implication of relativity is philosophical. If time can tick at different rates for different observers, then what does now really mean? Is there a universal present that everyone shares? The answer, according to relativity, is no. What one person considers the present may be in the past or future for someone else, depending on their relative motion. Events that are simultaneous for one observer may not be for another. This shatters our everyday understanding of cause and effect, past and present. It suggests that time is more like a landscape than a flowing river, a dimension you can move through, depending on your perspective. This has led some physicists and philosophers to support a view called block time, where past, present, and future all coexist. In this view, time doesn't flow, it just is. Everything that has ever happened or will happen already exists in the fabric of space-time. From this perspective, the future is not open or undecided. It's already there, waiting for us to arrive. This idea is unsettling, as it undermines our belief in free will and the openness of the future. But it's consistent with what relativity tells us. In a universe where time isn't universal, the story may already be written. And yet, despite these mind-bending revelations, our day-to-day experience of time remains largely unchanged. We still wake up, watch the seconds tick by, and feel the minutes pass. But beneath the surface of our lived experience, time is far stranger than it seems. Every moment we spend here on Earth is shaped by gravity, velocity, and the warping of space-time. The very act of aging, of growing older, is different for someone flying in orbit than for someone standing still on the ground. We are all time travelers of a sort, moving at slightly different rates depending on our circumstances. Einstein's insights didn't stop at revealing these effects, they opened the door to deeper questions. Could time be manipulated? Could we travel forward or backward through it? While relativity allows for forward time travel, moving rapidly through space to experience less time, it makes backward travel far more problematic. Closed time-like curves, wormholes, and exotic matter remain largely theoretical. And yet, the physics that governs time continues to hint at possibilities far beyond what we understand today. The more we learn, the more we realize how little we truly know. It's humbling to think that the universe is so fluid, so flexible in its construction. We are no longer at the center of a fixed cosmos, ticking along with the divine metronome. Instead, we exist in a reality where time can stretch and compress, slow down and speed up, depending on how and where we move. The clock on the wall is not the final authority. It's only a local measure of a deeper, more mysterious rhythm that pulses through space-time itself. Time isn't universal, and because of that, neither are we. So the next time you glance at a clock, take a moment to remember that your experience of time is unique, not just metaphorically, but physically. Your heartbeat, your aging, your memories, they are unfolding on a timeline shaped by your velocity, your altitude, and the invisible gravity holding you down. You are drifting on a current of time that is not the same for the person across the room, or the satellite above your head, or the astronaut orbiting a distant moon. Time is personal. Time is relative. And because of that, the universe is a far more fascinating place than we ever imagined. Simultaneity is relative. Imagine standing still and watching two lightning bolts strike the ground, one to your left, one to your right. You see them flash at the exact same moment. To you, the strikes are simultaneous. Now, imagine someone else speeding past you on a train. They also see the two flashes, but they don't agree that the strikes happened at the same time. One flash came a bit earlier, the other a bit later. You both saw the same event, but strangely, you don't agree on the timing. This isn't a trick of perception. It's a fundamental truth about how the universe works. According to Einstein's theory of relativity, simultaneity is not absolute. It's relative. The idea that there's no universal now shakes the foundations of our common understanding of time. In everyday life, we assume that events happening at the same time, anywhere in the world or universe, are truly simultaneous. We picture a kind of cosmic clock ticking in unison for everyone everywhere. But relativity tells us that this isn't how time behaves. Whether two events occur simultaneously depends entirely on your frame of reference, your state of motion. Time and space are tangled together, and the separation of events in both is not the same for everyone. To understand this, we have to look at what Einstein discovered in his theory of special relativity. One of the postulates of this theory is that the speed of light is always constant, no matter how fast you're moving. This sounds simple, but it has radical consequences. For the speed of light to remain constant for all observers, the fabric of space and time must adjust. Distances contract. Time dilates, and crucially, events that seem simultaneous in one frame of reference may not be in another. There is no universal agreement on what now means. Let's return to the lightning strikes. You, standing on the platform, are an observer at rest. You see the two flashes at equal distances, and they reach you at the same moment. You conclude they must have occurred simultaneously, but someone on a moving train sees those same flashes while they themselves are in motion. Because they're moving toward one flash and away from the other, the light from the flash ahead reaches them sooner than the light from behind. From their perspective, the events are not simultaneous, they happened at different times. Both observers are correct, according to their own reference frames. This thought experiment, first described by Einstein himself, demonstrates how simultaneity isn't a feature of the external world, but something that depends on motion. It shows us that now is a slippery, subjective concept. It's local, not global. What is now for one observer might be the past or future for another. In this way, special relativity collapses the idea of a shared present across the universe. It tells us that we cannot talk about what's happening right now on a distant star, because that notion depends entirely on how we're moving in relation to that star. This may seem like a subtle point, but it has deep implications. It's more like a personalized path through spacetime, different for each observer depending on their velocity and position. Two people, even if they meet at a point in space, may carry very different notions of which events were simultaneous just moments before. And the farther apart events are in space, the more disagreement there can be about their temporal order. Past, present, and future begin to blur. In classical physics, time was absolute. It marched forward uniformly and consistently for all observers. Newton pictured time as a separate backdrop, an independent stage on which the universe acted. But Einstein showed that time and space are not separate, they are linked. Space can stretch and bend, and so can time. The loss of absolute simultaneity was one of the most revolutionary consequences of that realization. It tells us that reality itself is not one fixed movie playing out in sync. Instead, it's a mosaic of different viewpoints, each slicing space-time in its own unique way. These insights are more than just theoretical. They affect real technologies. For example, when synchronizing clocks on Earth with those on satellites in orbit, scientists must account for these relativistic effects, including the relativity of simultaneity. Without these corrections, our global positioning systems would be wildly inaccurate. It's easy to forget that our understanding of simultaneity isn't just philosophical, it's practical. It's built into the equations guiding our spacecraft, our communication systems, and even our scientific experiments. Relativity isn't just about strange effects at high speeds. It's a reality that lives in the devices we use every day. But relativity of simultaneity also stretches into the philosophical. If there's no universal now, then what does it mean to exist in the present? What does it mean to say that something is happening right now elsewhere in the cosmos? In relativity, there's no privileged frame that defines what now truly is. Each observer draws their own slice through space-time. This means the universe doesn't unfold like a single story. Instead, it's more like a library of overlapping narratives, each with its own ordering of events. This leads to the concept of the block universe, a perspective in which all events, past, present, and future, coexist. In the block universe, time is treated like space. Just as the entire landscape of a map exists, even if you're only standing on one point, the entire timeline of the universe exists, even if you're only conscious of this one moment. There is no privileged now. There is just your now. Every point in time is simply another location in space-time. We move through it with awareness, but the structure itself doesn't flow. It just exists. For many, this idea is unsettling. It seems to rob the present of its specialness and the future of its openness. But from a relativistic standpoint, it's consistent. When simultaneity is relative, it becomes meaningless to ask what's happening now in a distant galaxy. That question has no answer unless you specify a frame of reference. And once you do, another observer can pick a different frame and disagree. Both will be right. Reality, then, is not a single thread of time, but a tapestry of perspectives. It also challenges the notion of causality. In relativity, if two events are separated by a distance that light cannot cross between them in time, then their order can flip depending on your motion. That means neither can influence the other. The laws of physics ensure that causality is preserved. No information can travel faster than light, but the order of unrelated events becomes ambiguous. One observer may see one happen first, another may see it happen second. Reality doesn't protest. Both timelines are valid within their own domains. All of this shifts how we see ourselves. We no longer live in a neatly ticking universe where past and future are clear and absolute. Instead, we live in a universe woven from the threads of many timelines, each one as real as the next. Our perception of the present is deeply local. Our experience of time is shaped by how we move and where we are. And that means our understanding of now is not a window into a global truth, but rather a reflection of our own motion through the cosmic sea. Next time you check the time, remember that you are syncing your local clock, not with some cosmic master clock, but with a shared convention designed for convenience. Deep down, time is not synchronized across the cosmos. What you experience as a shared moment may not exist at all for someone flying past you at great speed. The universe doesn't offer a single stage for events to occur in unison. It offers countless stages, each tilted in its own way, each one valid, each one real. In this strange and beautiful reality, even something as fundamental as simultaneity must bend. The more we discover, the more we see that the universe is not beholden to our intuitions. Time, it turns out, is not a river flowing equally through all lands. It is a twisting path, unique to each traveler. And now is just the name we give to the part of that path we are currently walking. The universe has no center. When we picture the Big Bang, we often imagine a fiery explosion bursting outward from a single point, scattering matter into a vast, empty void. It's a natural image, something detonating in the darkness, flinging stars and galaxies away from a central origin. But this picture, while dramatic, is deeply misleading. The Big Bang wasn't an explosion in space. It was the expansion of space itself, not from a single point into the void, but everywhere all at once. And because of this, the universe doesn't have a center. It never did, and it never will. This can be a difficult idea to grasp, because our everyday experience tells us that every explosion has a center. A firecracker bursts from a specific place. A ripple in a pond begins where the stone hits the water. But the Big Bang wasn't like that. It didn't happen in one location, sending matter flying into empty space. It happened to space itself. In the earliest moments of the universe, space was incredibly dense, incredibly hot, and extremely uniform. And then it began to expand, not into anything, but from itself, stretching and cooling as it went. Imagine blowing up a balloon. As you inflate it, every point on the balloon's surface moves away from every other point. There is no special location on the balloon's surface that can be called the center of the expansion. That center exists only in a higher dimension inside the balloon, but not on the surface itself. Our universe works the same way. If we picture the cosmos as a three-dimensional balloon being inflated in four-dimensional space, we see that the expansion happens uniformly. No matter where you are in the universe, you'll observe galaxies moving away from you, and every point will appear to be the center. That's the strange part. No matter where you go in the universe, it will look as if the universe is expanding around you. This isn't because you're in a special location. It's because space itself is stretching, and every observer sees distant galaxies receding. There's no privileged viewpoint, no cosmic bullseye. The illusion of centrality is a result of the uniform expansion of space. From Earth, we see galaxies fleeing in all directions. But if we were on another galaxy billions of light years away, we'd see the same thing, galaxies fleeing from that point too. When astronomers say the universe is expanding, they don't mean that galaxies are flying through space like cosmic shrapnel. They mean the space between galaxies is expanding. Imagine dots drawn on a rubber sheet. As the sheet stretches, the dots move apart, not because they're moving on their own, but because the surface between them is growing. In our universe, it's the fabric of space that's expanding, carrying galaxies with it. And since this stretching happens everywhere, every galaxy observes the same basic pattern, neighbors drawing apart with no central anchor. This realization has transformed our understanding of the cosmos. The universe isn't a bubble expanding into some empty realm beyond. There is no outside the universe. Space doesn't need anything to expand into. It is the thing that's growing. The Big Bang didn't happen at one point in space. It happened to all of space. Every region we observe, no matter how far, began as part of that same primordial moment. Every point was once compressed together in an unfathomably small volume, and from that timeless state, the cosmos began to unfold. This view is supported by the cosmic microwave background, the faint afterglow of the Big Bang. This radiation bathes the universe uniformly in every direction. It's the echo of a time when the universe was hot, dense, and opaque. Now, billions of years later, it has cooled and stretched into microwaves. The astonishing thing is that we observe this glow uniformly, no matter which way we look. That's not what we'd expect if the Big Bang had happened in a single location. But it makes perfect sense if space itself expanded from a uniform state. It's more like bread dough rising with raisins embedded in it. The raisins move apart not because they're pushing outward, but because the dough is swelling between them. And this brings us to a deeper truth. There is no center of the universe, because the universe is all there is. Every point is as valid as every other. We don't live near the middle, nor near the edge, because there is no edge. The universe, as far as we can tell, is either infinite or curved in such a way that it has no boundaries. And if there's no edge, then there can't be a center either. You can't draw a bullseye on something that has no outside and no boundary to anchor it. This realization humbles us. For centuries, humans believed Earth was the center of everything. Then we learned our planet orbited the sun. Later, we discovered our sun was just one star among billions in the Milky Way. Then came the revelation that our galaxy was just one of countless others. And now, relativity and cosmology tell us there's no center at all, no favored place. The cosmos doesn't revolve around us. It doesn't revolve around anything. It simply expands. But even though we've been dethroned from the center, we've gained something greater, a clearer understanding of the unity of all things. If every point was once in the same place, then everything shares a common origin. The atoms in your body were forged in stars, which formed from clouds birthed by the Big Bang. The distant galaxies we see in the night sky aren't foreign, they're kin. Their light has traveled across eons to reach us. And in that light, we see not just distant worlds, but a memory of our own beginning. It also changes how we think about movement and direction. There's no absolute up or down in the universe, no fixed point to measure against. In an expanding universe without a center, direction becomes relative. We define positions not by a cosmic origin, but by our relationships to each other. The further you look, the older the light becomes. The deeper you peer, the closer you get to the beginning. But no matter where you are, the view tells the same story. Of space stretching, of galaxies drifting apart, of time unfurling from a hot, dense seed. Even our concept of time is shaped by this expansion. The universe isn't just growing in space, it's aging in time. As it expands, it cools, evolves, and structures begin to form. Stars, galaxies, planets, and eventually life. Time, like space, is part of the cosmic fabric that unfolded from the Big Bang. And every clock in the universe, every heartbeat, every second that passes, is a measure of that unfolding. But since the expansion has no center, no single place ages differently. The entire universe has evolved as one, though different regions may look older or younger based on their distance and the light we receive. When people ask where the Big Bang happened, the only honest answer is everywhere. It happened here. It happened a billion light years away. It happened in the space your hand now occupies, and in the space between stars. The early universe wasn't a point in a void, it was the whole of space compressed. There was no outside, and there's no center now, just as there wasn't then. Every place is the center of its own observable universe, defined by the distance light has had time to travel since the beginning. This leads to another profound consequence. From every galaxy, the universe looks like it's expanding away from that point. This isn't because each galaxy is special. It's because expansion occurs uniformly. The same way dots on an inflating balloon move away from each other equally, galaxies recede in all directions, depending on how far they are. The further they are, the faster they appear to move away, a relationship called Hubble's law. And just like that, every observer sees themselves at the apparent center of motion, not because they are, but because the cosmos has no center at all. This concept is difficult at first, because it defies the way our minds evolved to think. We expect things to have beginnings in time and space. We look for centers, edges, directions. But the universe asks us to think bigger. It asks us to abandon the search for a central point and instead embrace the idea that the whole is the center, that there is no special place, only a grand symmetry that includes all things equally. The absence of a center doesn't mean chaos. It means balance. It means the laws of physics apply everywhere, not just here. It means the universe is not built around one location, but built of one fabric, unfolding with the same elegance in every direction. Whether we look left or right, deep into the night sky or inward into our own atoms, we are seeing different reflections of the same truth. The cosmos is expanding, and we are a part of that story, not the focus of it. So the next time someone asks where the center of the universe is, you can smile and say, it's everywhere and nowhere. The universe expands not from a place, but from a state. And in that expansion, we find not just scientific truth, but a kind of poetic humility. We are not the center of the universe, but we are part of it, born from its beginning, carried by its unfolding, and forever woven into the fabric of a cosmos with no edges, no anchor point, and no center at all. Most of the universe is invisible. We gaze up at the night sky and marvel at the stars. We see galaxies spiraling in the distance, nebulae glowing with color, and supernovae exploding with blinding brilliance. Our telescopes can peer back billions of years, capturing light that has traveled across the vast cosmic ocean. And yet, all this beauty, all this visible matter, makes up only a tiny fraction of what the universe truly is. The stars, the planets, the gas, the dust, everything we've ever observed accounts for less than 5% of the universe. The rest remains hidden, mysterious, invisible. Roughly 27% of the universe is composed of something we call dark matter. It's not dark because it's colored black. It's dark because it doesn't emit, absorb, or reflect light. We can't see it directly. It doesn't shine or glow or leave a trace in our detectors, but we know it's there because of what it does. Galaxies spin too fast to be held together by visible matter alone. Stars at their edges should be flung into space. And yet they remain. Something unseen is holding them together. Something massive. Something invisible. Then there's the other mystery, something even stranger than dark matter. Nearly 68% of the universe is made of something called dark energy. While dark matter pulls things together, dark energy does the opposite. It pushes. It stretches. It drives the accelerated expansion of the universe. We expected the expansion to slow down over time, pulled back by gravity. But observations show the opposite. Galaxies are not just moving away from each other, they're doing it faster and faster. Something is fueling this acceleration, and we don't know what it is. Combined, dark matter and dark energy make up about 95% of the universe. That means everything we've ever studied, all of chemistry, physics, astronomy, and biology, has focused on just a sliver of reality. The rest lurks in the shadows, whispering to us only through subtle gravitational clues. It's like trying to understand an ocean by examining a handful of foam. We are adrift in a sea of the unseen, surrounded by forces and particles we can't yet explain. Dark matter reveals itself most clearly through gravitational lensing. When we observe light from distant galaxies passing by massive clusters of matter, we see the light bend. This bending is a result of gravity, but in many cases, the amount of visible matter isn't enough to cause the observed distortion. Something more must be there, bending space itself. That something is dark matter. It acts like an invisible scaffold, shaping the structure of the cosmos. Without it, galaxies wouldn't form, stars wouldn't cluster. The universe would be a very different place. Scientists have tried to detect dark matter directly. They've built underground detectors, shielded from noise and radiation. They've watched for elusive particles that might interact with ordinary matter in rare, subtle ways. And while there have been hints and anomalies, the truth remains elusive. Dark matter doesn't play by the rules we expect. It slips through our instruments like a ghost. We have ruled out many possibilities, but what remains is a riddle that defies resolution. It's possible dark matter isn't made of particles at all. Perhaps it's something we haven't even thought to imagine. Dark energy is even harder to grasp. While dark matter clusters around galaxies and pulls them together, dark energy is smooth, uniform, and repulsive. It doesn't clump. It doesn't gather. It acts like a pressure woven into the fabric of space-time itself. It was first discovered in the late 1990s, when astronomers studied distant supernovae and found that the universe's expansion was accelerating. This was a shock, a complete reversal of what we thought we understood. And from that unexpected result came the realization that most of the universe is made of something we don't understand at all. Some believe dark energy may be related to the cosmological constant, an idea Einstein once introduced and later called his greatest blunder. The constant represents a kind of energy intrinsic to space. If it's real, then the vacuum of space isn't truly empty. It's charged with a hidden energy that pushes outward. Others believe dark energy may arise from a new kind of field similar to the Higgs field, permeating all of space. Still others suggest it may point to a deeper flaw in our understanding of gravity itself. But so far, no theory has provided definitive answers. These mysteries remind us how little we truly know. For all our progress in science, we remain in the dark, literally. The cosmos we observe is just the tip of the iceberg. The real substance lies hidden beneath the surface. It bends light, accelerates expansion, and sculpts galaxies, but remains invisible to every telescope we've ever built. It humbles our ambitions and invites deeper curiosity. It whispers that the universe is more complex than we imagined, and that the greatest discoveries may still lie ahead. And yet, there's beauty in the unknown. There's something wondrous about living in a universe that still hides its secrets. The fact that dark matter and dark energy exist at all means we are part of a story still unfolding. Our instruments grow more precise. Our questions grow sharper. And with every new observation, we peel back another layer. We may not yet know what dark matter is made of. We may not understand the nature of dark energy, but we know they are there. And that knowledge is a light in the darkness. Dark matter and dark energy don't just affect distant galaxies. They affect us. They influence the structure of the universe we live in. Without dark matter, the Milky Way would have never formed. Without dark energy, the universe might have collapsed in on itself long ago. We owe our existence to these invisible forces. We live in the balance between them, between the pull of dark matter and the push of dark energy. Our world, our lives, and everything we know are shaped by forces we cannot see. It's tempting to imagine the universe as mostly empty. We float through space thinking of the void as a vacuum. But in truth, the universe is full of fields, full of particles, full of energy. We just haven't learned how to see it yet. Our eyes evolved to detect light. Our senses evolved to survive here on Earth. But the universe is not limited to what we can see. It's bigger, stranger, and more beautiful than we've dared to dream. The search continues. New telescopes are being launched, new detectors are being built. Projects like the James Webb Space Telescope, the Vera Rubin Observatory, and the Euclid mission are all designed to help unravel the nature of dark matter and dark energy. They will look deeper into the past, map more galaxies, and test our theories against the light of ancient stars. With every data point, we move closer to understanding what the universe is really made of. And perhaps, one day, the invisible will become known. Until then, we live in a cosmos shaped by shadows, a universe ruled by things we cannot touch or see. And yet, those invisible forces are not our enemies. They are the context of our being, the stage on which life unfolds, the scaffolding that built the stars, the breath that inflates the void. We are not separate from these mysteries. We are part of them, carried along by currents we barely understand, living in a universe that is mostly unseen and entirely miraculous. Quantum superposition. Imagine a world where something can be here and not here, where a single particle can exist in two states at once, where reality, at its most fundamental level, is not definite, but smeared across possibilities. This isn't science fiction. It's the strange and unsettling reality of quantum mechanics. And at the heart of this mystery lies a concept that breaks all classical expectations: quantum superposition. In the everyday world, things have a location. They have a state. A light is either on or off. A coin lands heads or tails. A cat is either alive or not. But in the quantum realm, the domain of atoms, electrons, and photons, these rules fall apart. A particle like an electron doesn't choose a single path. It can exist in a superposition of paths. It doesn't spin in one direction. It spins in both directions at once. It doesn't travel through one slit. It travels through every slit simultaneously. Until we look. This is the essence of quantum superposition. A particle doesn't occupy a single state until it is measured. Before observation, it exists in all possible states at once, overlaid like musical chords. Not because we lack information, but because reality itself hasn't decided. The quantum world doesn't deal in certainty. It deals in probability, in potential, in wave-like possibilities that only collapse into one outcome when we intervene. Let's take the classic example, the double-slit experiment. Fire a single electron at a barrier with two slits, and on the other side, detect where it lands. You might expect the electron to go through one slit or the other, but something astonishing happens. If you don't observe the slits, the electron behaves like a wave. It passes through both slits. It interferes with itself. The result is an interference pattern, peaks and troughs of probability, as if the electron explored every path. But the moment you try to measure which slit it passed through, the pattern collapses. The wave becomes a particle. The superposition ends. Why? This is the heart of the quantum riddle. Until we observe, the particle is in a superposition, a mix of all possible states, but measurement forces it to choose. It's not just that we don't know what state the electron is in. It's that there isn't a definite state. Reality at that level is fundamentally indeterminate. Our classical mind struggles to accept this. We want to believe the particle had a trajectory, a definite path, a truth waiting to be uncovered. But quantum mechanics says otherwise. Until measured, the question has no answer. Spin offers another vivid example. Electrons have a property called spin, which can be thought of as a kind of intrinsic angular momentum. When measured along an axis, the spin will be either up or down. But before the measurement, the electron doesn't simply have an unknown spin. It's in a superposition, both up and down at the same time. Only when we measure do we get one outcome. And this isn't due to some hidden variable lurking beneath the surface. The uncertainty is built into nature itself. This was the idea that unsettled even Einstein. God does not play dice, he famously objected. He believed there had to be a deeper reality, hidden variables that, if known, would restore determinism. But experiment after experiment, including tests of Bell's theorem, have shown that quantum mechanics cannot be explained by hidden variables, at least not local ones. The universe really does behave probabilistically. And superposition is not just a mathematical trick. It reflects something profoundly real. Quantum superposition isn't limited to electrons or photons. It applies to every particle in the universe. But as objects become larger and more complex, their quantum behavior becomes harder to maintain. Interaction with the environment causes decoherence, the collapse of the superposition into a single state. That's why we don't see chairs or trees in two places at once. Their quantum states are constantly being observed by their surroundings. But in isolated systems, we can preserve superpositions and even use them. This is the foundation of quantum computing. In classical computers, bits are either 0 or 1. But quantum bits, qubits, can be in a superposition of both 0 and 1 at the same time. This allows quantum computers to process an enormous number of possibilities simultaneously, giving them a kind of parallelism classical machines can't match. By exploiting superposition, entanglement, and interference, quantum computers promise to revolutionize fields like cryptography, simulation, and optimization. But quantum superposition also leads to paradoxes. Consider Schrödinger's cat, the famous thought experiment. A cat is placed in a box with a quantum device that has a 50% chance of releasing poison. Until the box is opened, the quantum system is in a superposition of decayed and not decayed. But what about the cat? Is it alive or dead? According to quantum logic, the cat is in a superposition, both alive and dead, until we look. This isn't about cats. It's about scale. How far does superposition go? Can it apply to macroscopic objects, to consciousness itself? No one knows for sure. Some interpretations, like the Copenhagen interpretation, say the wave function collapses upon measurement. Others, like the many-worlds interpretation, suggest that all outcomes happen, and we simply find ourselves in one branch. In that view, the superposition never collapses. Instead, the universe constantly splits into countless versions, each one containing a different outcome. In one, the particle goes left. In another, it goes right. In one, the cat lives. In another, it dies. Superposition blurs the line between possibility and actuality. It tells us that reality doesn't crystallize until it's measured. It challenges our deepest intuitions. It suggests that the world isn't made of things but of probabilities. That the electron isn't a tiny ball moving through space, but a spread of possibilities, a cloud of potential, a waveform waiting to be collapsed by observation. The universe, then, is not a static machine ticking along. It's a theater of becoming, unfolding only as we engage with it. Even time itself begins to lose its classical meaning. If particles can exist in superpositions of states, what about events? Can causes and effects be superposed? Can the order of operations be indefinite? Experiments suggest that in certain quantum systems, yes, processes can occur in a superposition of sequences. The implications are staggering. Reality may not be composed of fixed chains of events, but of entangled possibilities, waiting to be unspooled. So what is superposition really? It's not an illusion. It's not a lack of knowledge. It's a feature of reality, confirmed by countless experiments. It's the reason lasers work. It's the reason electrons don't spiral into atoms. It's the engine behind quantum entanglement, teleportation, and computing. And yet, it resists our efforts to visualize it. There's no metaphor that fully captures what it means for something to be two things at once. It exists only in the math, and in the strange, flickering edge where reality hasn't yet made up its mind. And perhaps that's the point. Superposition invites us to loosen our grip on certainty, to accept that the universe doesn't owe us clarity. It only offers patterns, probabilities, and unfolding truths. In the quiet realm beneath perception, particles dance in possibility. They whisper of paths not taken. They defy categories. They invite us to wonder. So the next time you flip a coin or look at the stars, remember this: the universe isn't built from solid pieces, arranged like Lego bricks. It's built from waves of chance, from states that are neither this nor that, but both. From a silence where possibility reigns. And in that silence, before the collapse, everything is still undecided. Everything is still possible. Quantum entanglement. At the heart of quantum mechanics lies a phenomenon so strange, so unsettling, that even Einstein couldn't accept it. He called it spooky action at a distance, the eerie ability of one particle to instantly influence another, no matter how far apart they are. This phenomenon is known as quantum entanglement. It isn't just an oddity. It's one of the most profound features of the universe, and it breaks the classical rules of space, time, and logic. In the classical world, objects have clear identities. They exist independently. What happens here cannot instantly affect what happens over there. Information must travel through space, constrained by the speed of light. That's the rule. That's causality. But quantum entanglement violates this intuition. When two particles become entangled, they form a shared state. Measure one, and the other's state is instantly revealed, even if it's light years away. It's not a signal. It's not a trick. It's nature. And it forces us to question the very structure of reality. Imagine two electrons born from the same event, like twins separated at birth. Their spins are entangled. If one is found to be spinning up, the other must be spinning down. But until you measure them, neither has a definite spin. They exist in a superposition, both up and down at once. It's only when you measure one that the entangled state collapses, and the other's state becomes fixed as well, instantly, no matter the distance, no matter the separation. This isn't just theory. It has been confirmed again and again. Physicists have separated entangled particles by miles, even placing them on opposite sides of the planet. The result is always the same. When one particle is measured, the outcome of the other is determined instantly. There's no delay, no signal traveling between them. It's as if space itself doesn't matter, as if the two particles are part of a single, inseparable system stretched across the void. Einstein couldn't accept this. He believed quantum mechanics must be incomplete. He suspected there were hidden variables, information buried inside the particles, determining their states in advance. In this view, the particles weren't changing upon measurement. They were simply revealing what was already there. But then came Bell's theorem, a revolutionary insight. It showed that no hidden variable theory could explain the results of entanglement experiments unless it allowed for non-locality, instantaneous connections. Bell's inequality gave us a test, and experiments have shown that entangled particles really do behave in ways no classical system can explain. So what does this mean? It means that quantum mechanics isn't just weird, it's non-local. The properties of a system can be shared across space. Two particles can be bound by a relationship that transcends distance. They are not two things. They are one, split across space. Measure one, and you collapse the state of both. The universe, it seems, is more deeply connected than we ever imagined. This doesn't mean information is traveling faster than light. That would violate special relativity. Entanglement doesn't allow us to send messages instantaneously. It doesn't enable faster than light communication, but it does suggest that reality itself is more entangled than separate, that the division between here and there is not absolute, that what we call locality, the idea that things only influence their immediate surroundings, is an illusion at the quantum level. The implications ripple through science and philosophy. Entanglement raises questions about causality, determinism, and the nature of identity. If a particle here can be connected to one across the universe, then space is not a barrier. And if their states aren't defined until measured, then reality is not fixed, but codependent. The universe doesn't just contain objects. It contains relationships, webs of entanglement that bind the cosmos into a whole. Some interpretations of quantum mechanics suggest that entanglement is just a reflection of information, correlation, not causation. Others argue that entanglement points to a deeper reality, one in which space and time are emergent, not fundamental. In these views, what we experience as space may arise from entangled quantum states. The structure of the universe may be more like a vast entangled network, a cosmic fabric of interdependent quanta. And this isn't just philosophical musing. Entanglement has practical applications. It forms the foundation of quantum cryptography, where secret keys can be shared securely between distant parties. It's the basis for quantum teleportation, where the state of a particle is transmitted from one place to another using entanglement and classical communication. It may even enable the quantum internet, a global network powered by entangled connections. But the most breathtaking idea is perhaps this: entanglement could be the key to understanding space-time itself. Some physicists believe that space is nothing more than a web of entanglement, that the geometry of space arises from the pattern of connections between quantum systems. In this view, distance is not a physical stretch. It's a measure of entanglement. The more entangled two regions are, the closer they are. If this is true, then entanglement doesn't just act within space, it creates space. This flips our intuition. We think of space as the container in which events unfold, but entanglement suggests the opposite. The universe may be a vast quantum system, and space is simply how that system organizes its relationships. The more we learn, the more we realize that reality is not built from things, but from connections, from correlations, from entangled states that blur the boundary between here and there. In the language of quantum theory, the universe is not a machine but a melody, not a structure but a song. And each entangled particle is a note in that song, resonating with its counterpart, even across unimaginable distances. The music of the cosmos is not local. It is non-local, and its harmony echoes through every quantum interaction. So what are we to make of this? How do we live in a universe where particles influence each other beyond space, where the act of observation determines outcomes, where cause and effect are not so clearly defined? Perhaps the answer is not to solve the mystery, but to embrace it, to accept that at the deepest level, the universe is not composed of isolated fragments, but of unity. Entanglement teaches us that separation is an illusion, that distance is a construct, that reality is woven together, not broken apart. We are not alone. We are entangled with each other, with the stars, with the quantum foam of the early universe. Every particle in your body may have once danced in entanglement with particles now light years away. So the next time you look up at the night sky, remember what you see is not far, not truly. The photons that reach your eyes are part of a vast quantum conversation, a dialogue that began at the birth of time and continues still. A universe stitched together by threads of entanglement, whispering across the darkness, not through space, but as space. The vacuum isn't empty. When we hear the word vacuum, we imagine emptiness, a void, a complete absence of matter, energy, and motion. We picture the space between stars as cold and silent, a black canvas on which the universe paints its structures. For centuries, empty space was thought to be just that, empty, a backdrop with no substance. But in the world of quantum physics, nothing could be further from the truth. The vacuum, as it turns out, is not empty. It's alive. It's restless. It teems with activity, even in the absence of matter and light. At the heart of quantum field theory lies a strange and beautiful idea. Every point in space, even the most desolate and abandoned, is filled with invisible energy. This energy doesn't come from atoms or radiation. It emerges from the very fields that define the universe. These fields, which extend throughout all of space, never truly rest. Even when no particles are present, the fields still fluctuate. They jitter. They vibrate. And out of these fluctuations, particles spontaneously appear and vanish, moment by moment. These are the virtual particles of the quantum vacuum. They're called virtual not because they're imaginary, but because they're fleeting, borrowing energy from the vacuum to exist for a moment, then disappearing before they can be directly observed. This constant, buzzing activity gives rise to what's called zero-point energy, the lowest possible energy a quantum system can have. It's never zero. Even in absolute darkness, even at absolute zero temperature, the vacuum still hums, still pulses, still lives. This strange energy has real, measurable effects. One of the most striking is known as the Casimir effect. Imagine placing two uncharged metal plates very close together in a vacuum, just a few nanometers apart. You'd expect nothing to happen. But quantum theory predicts, and experiments confirm, that the plates are gently pushed together. Why? Because the presence of the plates restricts the quantum fluctuations between them. Outside the plates, the vacuum vibrates freely. Inside, only certain wavelengths can fit. The imbalance creates pressure from nothing, and the plates move. This invisible force, born from the quantum vacuum, proves that space is not truly empty. Another sign of the vacuum's hidden power is the Lamb shift, a small difference in energy levels of hydrogen atoms caused by interactions with virtual particles in the surrounding vacuum. This effect, too, has been measured and confirmed. It's as if the atom is never alone. It's always whispering with the vacuum, always influenced by the endless dance of particles that come and go without a trace. Even empty space has a voice, faint but persistent. Some physicists describe the vacuum as a seething quantum foam. At the tiniest scales, far smaller than atoms, space is not smooth. It's turbulent, chaotic. Particles and antiparticles bubble into existence, annihilate, and vanish billions of times per second. Space itself, at the Planck scale, is wild and unpredictable. What appears calm and still at human scales is, beneath the surface, a boiling sea of uncertainty. This foam may even shape the structure of the universe at large. This idea that empty space is never truly empty has profound implications. It tells us that nothingness is not the absence of existence, but a kind of invisible fullness, a foundation of fluctuating fields that give rise to everything else. Matter and energy emerge from this background like ripples rising from the sea. Space is not passive. It's dynamic, and we are living in a universe that is filled with activity, even in its quietest corners. The quantum vacuum may also hold the key to one of the greatest mysteries in physics, dark energy. As the universe expands, it's doing so at an accelerating rate. Some physicists believe that this acceleration is driven by vacuum energy, an intrinsic pressure built into the fabric of space itself. If true, then the fate of the cosmos may be determined by the restless fluctuations of the quantum void. The vacuum, far from being empty, could be the most powerful entity in existence. And then there is the concept of vacuum decay, a chilling possibility predicted by certain theories. It suggests that our universe may exist in a false vacuum, a metastable state that isn't truly the lowest energy possible. If this is the case, then a quantum fluctuation, somewhere in the vastness of space, could trigger a transition to a lower energy vacuum. A bubble of true vacuum could expand at the speed of light, rewriting the laws of physics as it goes. Nothing could stop it. It would be the end of everything we know, not with a bang, but with a whisper from the vacuum itself. Despite its strangeness, we are learning to harness the vacuum. Technologies like quantum electrodynamics, the most accurate theory in history, rely on precise calculations involving vacuum fluctuations. Quantum computers are designed to manipulate quantum states that interact with the vacuum in delicate ways. In laboratories, physicists create conditions where the vacuum behaves in unexpected and exotic manners, revealing more of its hidden nature with each passing year. And yet, much remains unknown. What exactly is the vacuum made of? Is it a feature of quantum fields, of space, of something deeper? Some theories suggest the vacuum holds the secret to unifying gravity with quantum mechanics. Others propose that what we call space is a holographic projection encoded on a distant surface, and that the vacuum is a kind of emergent phenomenon. The more we probe, the more the line between something and nothing begins to blur. Even our language begins to fail. What do we call a place with no matter, no light, and yet endless activity? How do we describe a field that gives rise to particles without ever being seen? The vacuum defies our categories. It is not empty. It is not full. It is not nothing. It is not something. It is the ground state of reality, the silent stage upon which the universe performs its symphony. And perhaps that is the most poetic truth of all. The universe, it seems, does not need a cause to be filled. Even in the absence of matter, of light, of time itself, there is motion. There is potential. There is life. We live in a cosmos where even nothingness is alive with mystery, where stillness is an illusion, and the quietest spaces are filled with unceasing rhythm. In every corner of space, in every pause between stars, the vacuum pulses, the void breathes, and from its breath, all things come. So the next time you look into the night sky and see the darkness between the stars, know this: you are not looking into emptiness. You are looking into a sea of unseen activity, a realm more alive than silence. Every inch of space is filled with invisible storms. Every second, the vacuum gives rise to momentary particles, ghosts of reality that flicker into existence and then vanish. This dance of creation and annihilation is happening right now, all around you, even within you. You are made of particles that once emerged from this vacuum. You are the result of fluctuations, of ripples in the fields of existence. The atoms in your body, the forces that hold them together, the energy that animates your thoughts, all of it rests on the vacuum's invisible stage. And while you may not feel its presence, you are inseparable from it. You are a pattern in its wave, a moment in its song. The vacuum isn't empty. It never was. It is the quiet fire beneath all things. The observer effect, the measurement problem. In the quiet stillness of the quantum world, something profound happens when you look, when you measure, when you observe. The very act of observation does not simply reveal what is already there, it appears to shape what is real. In quantum mechanics, this is known as the observer effect, and it challenges the very foundation of how we think about reality. It's not just that we don't know what a particle is doing before we measure it, it's that it may not even have a definite state until we intervene. Reality, at its most fundamental level, seems to be waiting for us to look. This is the heart of the measurement problem in quantum mechanics. According to the theory, particles like electrons or photons don't exist in a single location or spin in one direction until they're measured. Before that, they exist in a superposition, a blur of all possible outcomes. The wave function describes this range of possibilities, but when we observe, something changes. The wave function collapses. The particle snaps into one reality, one position, one spin, one answer. But what causes this collapse? What transforms possibility into actuality? That question remains one of the deepest mysteries in physics. At first glance, the idea that observation changes reality sounds mystical or magical. But it's a mathematical fact built into quantum theory. It's not that human consciousness creates reality, necessarily, but that interaction, measurement, or entanglement with an outside system changes the quantum state. When we set up an experiment to measure a particle's position or momentum, we force nature to choose. Before that, there is only probability, only potential, only a cloud of outcomes waiting to be made real. Consider the famous double-slit experiment. Fire a single electron at a barrier with two slits. If you don't observe which slit it goes through, the electron behaves like a wave. It interferes with itself, passing through both slits at once. The result is an interference pattern on the screen behind. But if you place a detector at the slits, watching which path the electron takes, the interference disappears. The electron now acts like a particle, going through one slit or the other. The act of measurement collapses the wave function. The observer changes the outcome. But what counts as an observation? Is it the involvement of a conscious mind? Or is it simply the interaction with a measuring device? Most physicists lean toward the latter. Anything that forces the quantum system to interact with something classical, some definite, irreversible change in the environment can cause collapse. But this only raises more questions. Where is the line between quantum and classical? Between superposition and certainty? Between the possibility of all states and the actuality of one? This is the measurement problem in its full form. Quantum theory is incredibly precise. It predicts outcomes with astonishing accuracy, but it doesn't explain what causes the wave function to collapse. It doesn't tell us how or why potential becomes reality. The theory describes what happens when we measure, but it stays silent about what's happening in between. It gives us no clear picture of reality when we aren't looking. In a sense, it tells us everything except what reality is. Some interpretations try to explain this. The Copenhagen interpretation, one of the oldest, says that quantum mechanics is complete, but the wave function only represents knowledge or information. Reality isn't definite until we measure it, and asking about its state beforehand is meaningless. This view avoids philosophical complications, but leaves us wondering, is the moon there when no one looks? Other interpretations go further. The many worlds interpretation suggests that the wave function never collapses. Instead, all possible outcomes occur, but in separate, branching universes. In one universe, the electron goes left. In another, it goes right. In one, the cat lives. In another, it dies. Measurement simply tells us which branch we're on. The universe, then, is constantly splitting, endlessly dividing into parallel realities. There's no collapse, only divergence. Still others propose decoherence, a process where the quantum system becomes entangled with its environment, causing the appearance of collapse without needing an observer. In this view, measurement is just quantum entanglement on a large scale. As the system interacts with the environment, its delicate superpositions become scrambled, unreadable. What we see as collapse is simply the loss of coherent interference patterns. Yet despite these interpretations, the core mystery remains. Why does measurement change the system? Why can't we observe without interfering? Is it possible to ever know what's really going on behind the curtain of probability? Or is reality fundamentally unknowable, forever shifting under the spotlight of observation? The measurement problem forces us to confront a humbling truth. We may be part of the equation. In classical physics, we could step outside the system. We could be observers, watching from a distance. But in quantum mechanics, there is no outside. The observer and the observed are part of one inseparable process. To observe is to participate. To measure is to interact. To know is to change. This changes how we think about knowledge itself. If observation alters the observed, then knowledge is not passive. It is active, dynamic. It shapes the very thing it seeks to understand. In this way, quantum mechanics becomes not just a theory of particles, but a philosophy of interaction. It teaches us that we cannot remain untouched by the world we explore. And perhaps, at the deepest level, the universe is not made of solid things at all, but of relationships, of interactions, of entangled states that only reveal themselves in context. The particle has no position until it is measured. The photon has no path until it is caught. Reality is not a set of facts waiting to be discovered, but a set of possibilities waiting to be chosen. So what is reality then? Is it a cloud of probability that sharpens into form only when we engage with it? Is it an ocean of branches, each holding a different outcome? Is it a single unfolding narrative shaped by our questions, our instruments, our minds? No one knows for sure, but quantum mechanics forces us to rethink the nature of existence. It whispers that the universe is not a fixed machine, but a dance of possibilities, that what we see is not separate from what we do, that reality at its root is participatory. And in this mystery there is wonder, there is beauty in the uncertainty, the idea that the universe is not cold and passive, but warm and responsive, that it listens, that it changes when you touch it, that it holds its truths not as fixed laws, but as unfolding potential waiting for someone or something to ask the right question. So the next time you ponder a particle or wonder about the edge of space, remember this: what you see depends on how you look. What exists may depend on whether you ask. And even in the smallest corner of the quantum world, reality is not just out there, it is in between the system and the observer, between the question and the answer, between what is and what could be. Wave-particle duality. It begins with a simple question: what is light? For centuries, scientists debated whether light was a wave or a particle. Newton believed it was made of particles, tiny projectiles flying through space. Later, others like Huygens insisted it was a wave, rippling through some invisible ether. Each side had evidence. Each had experiments that seemed to prove their point. But the deeper science probed, the stranger the answer became, because light, and eventually all matter, turned out to be both, and neither, at once wave and particle, depending on how you ask. This is the mystery of wave-particle duality. We first saw wave-like behavior in light through interference and diffraction. Shine light through two closely spaced slits, and you don't get two bright spots on the screen behind. You get a pattern, a series of light and dark bands, where the waves cancel or reinforce each other. This is something only waves do. Ripples in a pond behave this way. So does sound. So does light. And so, for a time, light was considered a wave. But then came another revelation. When scientists studied the photoelectric effect, they found something unexpected. Shine light on a metal surface, and electrons are ejected. But not just any light. It must be of a certain frequency. No matter how dim or intense the beam, if the frequency is too low, no electrons emerge. This made no sense if light were purely a wave. But it made perfect sense if light came in packets, called photons, each with a specific amount of energy. The higher the frequency, the more energy in each photon. This explained the effect perfectly. Light, it seemed, was not just a wave. It was also a particle. Einstein helped make sense of this, suggesting that light comes in quanta, discrete packets of energy. Each photon carries a precise amount, depending on its frequency. This explained the photoelectric effect and earned him the Nobel Prize. But it also opened a door to something far stranger. If light was both wave and particle, what else might be? That question found its answer in the 1920s, when Louis de Broglie proposed a radical idea. If waves could act like particles, maybe particles could act like waves. Electrons, protons, even atoms, what if they too had a wavelength? At first it sounded absurd. Electrons were tiny bits of matter. They had mass, charge, momentum. Waves were extended, continuous, and spread out. How could something be both? But when scientists tested de Broglie's idea, they found he was right. Fire a beam of electrons at a double slit, and just like light, they form an interference pattern. Electrons, tiny, point-like particles, behave like waves when you're not looking too closely. They spread out, interfere, diffract. Yet when they hit a detector, they arrive as single points, as particles, as impacts. They land one by one, building up a wave-like pattern over time. It's as if each electron travels as a wave, but lands as a particle. This paradox is the essence of wave-particle duality. not just for light, but for all matter. The world we thought was made of solid, indivisible bits is also made of probability waves. Your hand, your eyes, the air, the stars, everything is composed of entities that behave like waves in motion and particles at rest. The deeper we look, the more we find that nature refuses to be boxed into a single category. So what then is an electron? Is it a particle, like a marble, or a wave, like a ripple? The unsettling answer is that it's neither. Or rather, it's both, depending on how you observe it. Set up an experiment to measure position, and it behaves like a particle. Set it up to observe interference, and it behaves like a wave. It's not switching between two forms. It's not pretending. It's existing in a way that doesn't match our ordinary understanding. It's quantum. In quantum mechanics, we describe these behaviors with a wave function, a mathematical entity that encodes the probabilities of finding a particle in different places or states. The wave function spreads out like a wave, describing potential outcomes. But when you measure, it collapses. The particle appears at a point. This collapse isn't random noise. It follows the probabilities laid out by the wave function. The outcome isn't predictable, but it's not without structure. The wave informs the particle, and the particle reflects the wave. Wave-particle duality also extends to the Heisenberg uncertainty principle, which tells us that we cannot know both a particle's position and momentum with perfect precision. The more we know about one, the less we know about the other. This is not due to faulty instruments. It's built into nature. Particles that behave like waves inherently lack definite boundaries. A perfectly defined position means an undefined momentum, and vice versa. The wave and particle are locked in an eternal trade-off. This duality lies at the foundation of quantum theory. It challenges our classical intuitions. In the macroscopic world, things are either here or there. A baseball doesn't diffract. A chair doesn't interfere with itself. But in the quantum world, everything is fluid. A particle is not an object with a single trajectory. It's a spread of possibilities, a wave of outcomes. And only when we measure do we find one. Yet this isn't just a philosophical curiosity. Wave-particle duality has real, measurable consequences. Technologies like electron microscopes rely on the wave nature of electrons to achieve high resolution. Quantum tunneling, where particles pass through barriers they shouldn't classically cross, depends on wave behavior. Even semiconductors and lasers exploit quantum duality to function. We live in a technological world built on a reality that defies common sense. But even after a century of quantum mechanics, no one fully understands what wave-particle duality means. Some physicists take it as a reminder that our classical concepts don't apply at the quantum level. Others search for deeper explanations, hidden variables, alternate universes, or a more fundamental theory. But the experimental results are clear. The duality is real. The mystery is in how we choose to frame it. There's a quiet elegance in this contradiction. The idea that light, so delicate, so fast, so ethereal, can crash into atoms like tiny bullets. That electrons, so solid, so charged, can diffract like ocean waves. The boundary between particle and wave is not a hard line. It's a curtain that shifts depending on how you look. Nature doesn't choose a form until you ask. And when you do, it answers with a paradox. So the next time you see a beam of light, or think about the electrons flowing through your phone, remember, they are more than particles. They are more than waves. They are the union of both, dancing on the edge of possibility. They are questions made physical, uncertainties made visible. The world is not made of objects, but of patterns, not of bricks, but of probabilities. And in that truth lies a deep, luminous mystery. Wave-particle duality tells us something profound. The universe is not what it seems. Beneath the surface of things lies a realm where certainty dissolves and identity becomes fluid, where light becomes matter and matter becomes light, where the deepest truths are not about what is, but what can be. A realm where every act of observation is a choice and every outcome is a slice of the infinite. The arrow of time is a mystery. We wake each morning in a world that feels orderly. The sun rises, clocks tick, memories form, and time flows from past to future. Broken things stay broken. Smoke drifts from fire but never unburns. We grow older, never younger. Time, for us, has a direction. An arrow. Forward. always forward. But when we peer deeper into the laws of physics, something strange emerges. Most of these laws, at their most fundamental level, make no distinction between past and future. They work just as well in reverse. And yet, our lived experience insists otherwise. This contradiction is known as the arrow of time, and it remains one of the greatest mysteries in all of science. The equations of motion that govern particles, Newton's laws, Maxwell's equations, even the Schrödinger equation of quantum mechanics, are time-symmetric. If you filmed the dance of atoms and played the tape backwards, the physics would still make sense. The forces would still balance. The trajectories would still align. Nothing in those laws says time must flow in one direction. To the math, past and future are mirror images. But to us, they are not. We remember yesterday, but not tomorrow. We cause the future, but not the past. Something breaks the symmetry. That something, as far as we know, is the second law of thermodynamics. It states that in any closed system, entropy, the measure of disorder, tends to increase over time. A dropped cup shatters, but the shards never reassemble themselves. Heat flows from hot to cold, but never the other way around. And once you mix cream into coffee, it never unstirs. Entropy grows, order declines, and this irreversible trend gives rise to the arrow of time we all experience. But even this law raises deeper questions. Why does entropy increase at all? After all, the molecules of a cup don't know they're supposed to scatter. The fundamental forces pushing them are still time reversible. The increase in disorder seems to arise not from the laws themselves, but from initial conditions, from how the universe began. If the universe started in a state of incredibly low entropy, then its natural tendency is to become more disordered. But that only pushes the mystery back a step. Why did the universe begin in such an ordered state? This question takes us to the birth of everything, the Big Bang. The early universe, despite being hot and dense, was remarkably smooth and uniform. That smoothness, counterintuitively, corresponds to low gravitational entropy. And from that improbable state, entropy has been rising ever since. Stars have formed, galaxies have clustered, black holes have grown, and time has flowed forward. But no one knows why the cosmos began in such an unusual, low entropy configuration. It's as if the universe rolled a cosmic dice and landed on the most orderly number possible. And from that singular starting point, the arrow of time was born. But there's another layer of mystery here. If entropy is the only thing breaking time symmetry, then what happens at the quantum level, where time seems even more fluid? Quantum mechanics allows for reversible equations too. And yet, when we observe a quantum system, when we collapse a wave function, the outcome seems irreversible. The measurement appears to lock reality into a specific state. Some physicists believe that decoherence, the entanglement of a quantum system with its environment, may be part of how time's arrow emerges. Others think the arrow is an illusion, something arising from how we process information, not a feature of physics itself. Philosophers and physicists alike have struggled with these questions. Is time fundamental, or is it emergent? Is it something that exists independently of matter and motion, or is it a byproduct of entropy and complexity? One idea is that the flow of time is tied to our own consciousness, to the way memory forms, how we perceive change, how we process cause and effect. Perhaps time feels like it moves forward simply because that's how our minds construct reality. But if so, then the arrow of time is subjective, a mental artifact, not a physical truth. Yet there are hints that time's arrow may be more than just psychological. In cosmology, we see its imprint in the expanding universe. As space stretches, matter cools and structures form. The direction of time aligns with the direction of expansion. Some theorists propose that this link isn't coincidental, that the expansion of space is directly connected to the increase of entropy, and thus to the arrow of time. Others suggest that in a contracting universe, time could run backward. That if the cosmos were to collapse in a big crunch, entropy might decrease, and the arrow could reverse. But this remains speculative. Another provocative idea is the two-headed time model, a theory that proposes the universe may have two time arrows pointing in opposite directions from a shared origin. From one perspective, entropy increases forward. From the other, it increases backward. In this picture, what we call the Big Bang is the middle, not the beginning. On either side of it, time flows away in both directions. Each half sees itself as moving forward in time, but to the other, it is going backward. This concept preserves time symmetry while explaining our experience, yet it raises as many questions as it answers. Meanwhile, black holes, those gravitational giants of entropy, may hold even deeper insights. According to theoretical physics, the surface area of a black hole's event horizon is proportional to its entropy. As black holes grow, their entropy increases. When they evaporate through Hawking radiation, that information may be scrambled, but not lost. This interplay between entropy, information, and gravity may hold the key to time itself. Some believe that to solve the mystery of the arrow, we must understand how quantum gravity works, a theory that doesn't yet exist, but is quietly being born. And then there's us, tiny, sentient clusters of atoms observing this cosmic drift. Our very existence is a product of entropy. Life feeds on gradients, on the difference between order and chaos. We are systems that locally decrease entropy, organizing matter, creating structure by expelling it elsewhere. Even our memories are imprints of entropy's path. We remember the past because it had lower entropy than the present. We imagine the future because it has not yet happened. But in a deep sense, this may all be built on the direction of disorder, not time itself. So what, then, is the arrow of time? Is it a fundamental aspect of reality? Or is it a consequence of initial conditions of entropy, of information and memory? Is the future truly open and the past fixed? Or is time a dimension like space, where all moments exist equally and we simply move through them? No one knows for certain. But what is clear is this: the arrow of time is not carved into the laws of physics. It emerges. It grows from the seeds of entropy. It unfolds like a path in a dark forest, lit only by the flames of increasing disorder. We walk that path because the universe began in an unlikely state, and every moment since has been a descent into deeper complexity, from clouds to stars, from dust to life, from stillness to awareness. And so we live in a world where eggs break, but don't unbreak, where snow melts, but never refreezes into its original shape, where we age, remember, hope, and change. The arrow of time flows through all of this, whispering that what is done cannot be undone, that the story always moves forward. Yet somewhere beneath that flow, in the hidden order of the cosmos, time may be still, or circular, or reversible. The universe may not care about before or after. It may only care about possibility, probability, and patterns. The arrow may be a shadow cast by entropy on the wall of our minds. And if that's true, then perhaps time is not a river, not a force, but a lens, a way of seeing, a framework we use to navigate a deeper mystery, a cosmos built not of clocks and calendars, but of waves, fields, and information. The arrow of time, then, is not just a puzzle in physics. It is a reminder of how little we truly understand, and how much there still is to discover. You are mostly empty space. Take a moment to look at your hands. They feel solid. You can touch them, press them together, knock them against the table. They carry weight, mass, and presence. You might believe they are made of tightly packed matter, substance upon substance. But the truth is far stranger than it seems. You, the table, the room you sit in, are all composed mostly of nothing. You are a ghost made of atoms, and atoms are, overwhelmingly, empty space. To understand this, we must shrink ourselves to an unimaginable scale. Picture an atom, the basic unit of matter. At the center is a nucleus, made of protons and neutrons. Orbiting far around it are electrons, tiny, light, fast-moving particles. Now imagine enlarging the nucleus to the size of a marble. On that scale, the nearest electron wouldn't be a few centimeters away. It would be several kilometers distant. Between the nucleus and the electron is a vast, silent emptiness, a gulf, a vacuum. This means that more than 99.9999999% of an atom's volume is empty space, not filled with hidden particles or secret stuff, just absence. So when you touch your hand to your face, what's really happening is not matter colliding with matter. It's electromagnetic fields repelling each other. The electrons in your hand are pushing against the electrons in your skin. The sensation of touch, the resistance you feel, is the result of invisible forces. Not contact, but interaction. In this way, the solidity of the world is an illusion, a useful one, a necessary one, but an illusion nonetheless. You are composed of atoms, and atoms are not little balls packed together. They are dynamic systems with dense centers and diffuse edges. Electrons do not orbit the nucleus like planets around a sun. Instead, they exist in probabilistic clouds, defined by wave functions, spread out, uncertain, never quite in one place. Their exact location can't be known, only predicted. So how does something so insubstantial feel so real? The answer lies in force, specifically the electromagnetic force. Electrons repel each other. When your hand gets close to another object, the clouds of electrons in the atoms begin to interact. The repulsion between them builds. You feel pressure, resistance, solidity, but no two atoms ever truly touch. At the atomic level, there is no direct contact, only forces pushing against forces, like magnets turned the same way. Even the atoms in your body are not static structures. The nuclei contain protons and neutrons, which themselves are made of quarks, bound together by the strong nuclear force. These subatomic particles occupy tiny regions, almost point-like compared to the size of the atom. Around them, electrons flit in and out of possibility, smeared through space. The atom is more a process than a thing, a dance of forces and probabilities, rather than a hard, indivisible core. And yet, somehow, this emptiness gives rise to everything you know. The chair beneath you, the screen in front of you, the beating of your heart, the thoughts in your mind, all made from particles that are mostly space. You are a structure of patterns, energy shaped by fields, held in place by invisible rules. You are not a solid object, but a collection of vibrating relationships, bound together by forces you cannot see. Even your mass is not as substantial as it seems. Most of the mass of protons and neutrons doesn't come from the particles themselves, but from the energy of the strong force that binds them. According to Einstein's famous equation E equals 2, energy and mass are interchangeable. The swirling motion of quarks, the tension in the fields, these give rise to what we call matter. You are energy made slow, motion made tangible. And in between all that energy, all those particles, lies silence, the vacuum, the void. And yet, even that vacuum is not truly empty. Quantum physics tells us that space itself is alive with activity. Virtual particles pop in and out of existence, borrowing energy from the void, creating fleeting moments of being before fading away. The emptiness within your atoms is filled with this restless quantum foam. Stillness, it seems, is an illusion too. So what does it mean to be mostly empty space? Does it mean you are less real, less solid? Or does it reveal something deeper? That substance is not what defines us, but structure. That identity arises not from packed material, but from the intricate architecture of fields and forces. You are not made of stuff. You are made of form. And that form, though built on emptiness, is astonishingly rich. We often think of emptiness as a lack, but in the quantum world, emptiness is potential. It is the stage upon which all things unfold. It is the silence that gives shape to sound, the canvas behind the painting. Without empty space, atoms couldn't exist. Electrons couldn't orbit. Light couldn't move. Life couldn't breathe. The vacuum within you is not absence. It is the very condition that makes existence possible. Even stars, even galaxies are mostly space. The Earth orbits the sun with vast emptiness in between. And even within the sun, atoms keep their distance. The entire universe is a grand illusion of density, a ballet of particles separated by light years of nothingness. But from this emptiness, structure emerges. Patterns arise, and consciousness blooms. You are mostly empty space, but so is everything. And from this shared emptiness, we are all connected. You are not isolated. You are part of a vast web of forms woven from the same cosmic fabric. The atoms in your body were forged in stars, hydrogen from the Big Bang, carbon from dying giants, iron from supernovae. These atoms, though mostly empty, carry history, memory, meaning, and together they make you. So the next time you feel your hand resting on a surface, remember that what you're feeling is not solidity, but interaction. Electrons refusing to share space, forces creating the sensation of resistance. You are not touching the world. You are meeting it through fields, through distance, through structure. And in that structure lies something beautiful, a profound elegance, that from emptiness can come form, that from form can come motion, that from motion can come life, and that from life can come awareness, the ability to look inward and discover that even the self is made of space. That being is not a wall of matter, but a wave of energy, a ripple of existence traveling through time. You are mostly empty space, but you are also order, harmony, a song composed of probabilities and repulsions, of mass and motion, of energy and elegance. And though your atoms never truly touch, their fields align, they resonate, they cohere. You are a miracle not of substance, but of structure, a ghost that feels solid, a whisper that walks, a lattice of emptiness that learned to think. Consciousness is a hard problem. You open your eyes and the world appears, vivid, rich, immediate. The warmth of sunlight, the scent of coffee, the sound of distant bird song. These sensations are not just data. They are experiences. They feel like something. This feeling, this inner life, is what we call consciousness. And while science has mapped the brain in exquisite detail, there remains one question it cannot yet answer. How does the firing of neurons give rise to the feeling of being? This is the hard problem of consciousness, arguably the greatest mystery in all of science. We know a great deal about the brain. We know that certain regions process vision, others process sound, others handle memory or emotion. We can observe patterns of electrical activity, trace the pathways of neurotransmitters, even manipulate thoughts and moods with drugs or stimulation. But none of this tells us why those processes should result in subjective experience, why red feels red, why pain hurts, why there is anything it is like to be you sitting there right now aware. This problem was named by philosopher David Chalmers in the 1990s to distinguish it from the easy problems of consciousness, how the brain integrates information, responds to stimuli, or regulates attention. Those are hard in practice but solvable in principle. But the hard problem is different. It asks not how the brain works, but why it feels like something from the inside. Why neural activity isn't just mechanical computation, but gives rise to an inner world, a world of qualia, the raw, felt qualities of experience. Why should a pattern of electrical signals be accompanied by the color blue, or the flavor of chocolate, or the ache of longing? These are not properties we can find in the neurons themselves. We can't slice into the brain and extract a thought. We can't isolate a feeling in a test tube. We can measure the mechanisms, but the experiences remain hidden, private, first person. Science works in the third person. Consciousness lives in the first. Some theorists believe consciousness is an emergent property, that when matter becomes sufficiently complex, experience arises, just as wetness arises from H2O molecules. But this analogy has limits. We can explain wetness in terms of physics and chemistry. We cannot yet explain consciousness in terms of biology. Complexity doesn't automatically imply awareness. A computer can process vast data, but it doesn't feel anything. So where does feeling begin? Others suggest that consciousness might be fundamental, a basic feature of the universe, like space, time, or mass. In this view, matter and mind are not separate, but two aspects of the same underlying reality. Some propose panpsychism, the idea that even the smallest particles may carry some form of proto-consciousness, not minds, not thoughts, but glimmers of awareness. If this is true, then consciousness doesn't emerge from matter. It's already there, woven into the fabric of existence. Then there's the idea of integrated information theory, IIT, which tries to quantify consciousness as the amount of information integrated in a system. According to AIT, consciousness arises when information is both richly differentiated and deeply unified. The more a system integrates information in an irreducible way, the more conscious it is. This theory gives us a possible measure, but it doesn't yet explain the why. It tells us where consciousness might exist, but not how it feels. Meanwhile, global workspace theory suggests that consciousness is what happens when information becomes globally available to various parts of the brain, when it enters a kind of mental stage, visible to the whole system. This explains certain patterns of attention and awareness. But again, it explains function, not feeling. It gives us a cognitive architecture, but not the inner glow. The hard problem remains because every explanation so far leaves out the key ingredient, subjectivity. You can describe the structure of a song, analyze its notes and rhythms, but that won't capture the experience of listening to it. or the emotion it stirs. Consciousness is like that, an interior, qualitative realm that defies objective capture. And yet, it is the most certain thing we know. Before we can know physics, chemistry, or biology, we must be conscious. We can doubt the world, but not the fact that we are experiencing it. In this sense, consciousness is not just a puzzle, it is the ground of all knowing, the light in which all questions are asked. Some philosophers have suggested that we need a radically new framework to understand consciousness, one that doesn't treat it as a byproduct, but as a central feature. Perhaps we are like fish trying to understand water, using tools built for everything but the thing that surrounds us most completely. Perhaps we need to rethink matter, not mind. There are even those who believe the hard problem may never be solved, not because it is unsolvable, but because it lies outside the scope of empirical science, that it belongs to philosophy, or introspection, or a domain yet to be defined. But this feels unsatisfying. For if consciousness is at the center of our lives, then understanding it may be the most human question we can ask. The mystery deepens when we consider altered states, dreams, meditation, psychedelics, anesthesia. In each case, the contents of consciousness shift or dissolve, and yet the fact of experience persists. Even in a dream, there is a dreamer. Even in silence, there is awareness of silence. This suggests that consciousness is not its contents, but the field in which contents arise, the space of knowing, the witness behind the thoughts. Some traditions, especially in Eastern philosophy, have long treated consciousness not as a product of the brain, but as the fundamental reality itself. In these views, the mind does not generate awareness, it filters it. The brain is not a creator of experience, but a lens. If the lens is damaged, the image is lost, but the light remains. Science has yet to confirm or refute these ideas, but they point to an important truth. Our understanding of consciousness is shaped by our assumptions. If we assume mind is secondary to matter, we look for neural correlates. If we assume matter and mind are two sides of a coin, we ask different questions. And if we assume consciousness is primary, we must rethink what we mean by reality. Meanwhile, artificial intelligence grows more powerful. Machines can speak, paint, even imitate emotion. But are they conscious? Or are they sophisticated reflections, mirrors without minds? Without qualia, there is no experience. Without experience, there is no self. And no matter how clever the simulation, the question lingers, is anyone home inside? The hard problem touches everything. It touches ethics, because consciousness defines who matters. It touches physics, because measurement depends on observation. It touches philosophy, because it defines what it means to exist. And it touches each of us, because we are not just thinking machines, we are aware. We suffer. We hope. We feel the world from the inside. So what are we? Are we brains in a vat, programs running in a biological computer? Or are we luminous centers of awareness, briefly lit within the void? Are we meat with minds, or minds inhabiting matter? We do not know. But the very asking of the question is a sign of consciousness, a flame that burns to know itself. In the end, the hard problem may not be solved by equations or scans. It may be understood only by looking inward, by witnessing the play of thought, the coming and going of sensation, the stillness behind perception. Science can measure the activity of neurons, but only you can feel what it's like to be you. And that experience, mysterious though it may be, is real. It is the only thing we can be completely certain of. So the next time you close your eyes, take a moment to listen, not to the world outside, but to the silence within, the awareness that knows you are here, the space in which thoughts arise. That presence is consciousness, and it is, for now, an unsolved miracle. Free will is debated. You wake up in the morning and make a decision, coffee or tea, left or right, stay or go. You feel as though you are choosing freely, that your will is your own. But beneath that comforting sense of control lies one of the deepest and most debated questions in all of philosophy, neuroscience, and physics. Do we really have free will? Or are we simply watching choices unfold, powerless to change the script? For centuries, the belief in free will has shaped our understanding of morality, responsibility, and the self. If we are free to choose, we can be held accountable. We are the authors of our own lives. But if our actions are determined by laws of nature, by prior causes, by unconscious impulses, then the story becomes more complicated. Are we truly in control, or are we passengers in a vessel guided by forces we cannot see? At the heart of the scientific challenge to free will is the principle of determinism. In classical physics, the universe is governed by precise laws. Given the exact state of a system now, its future can, in theory, be predicted perfectly. If the brain is a physical system, just atoms and forces, then our thoughts and actions might also be determined by the prior state of the universe. Every decision we make, under this view, is the inevitable result of what came before, like dominoes falling, like clockwork. But quantum mechanics seems to break this chain. At the smallest scales, particles behave unpredictably. Outcomes can't be known with certainty, only probabilities. Some see this quantum randomness as a door back to freedom. But randomness is not choice. If your decision is random, it's not free, it's arbitrary. Rolling dice in your head doesn't make you more responsible. It just changes the problem. Determinism may remove freedom, but so does pure chance. Then there's the challenge from neuroscience. In a series of groundbreaking experiments, researchers like Benjamin Libet discovered that the brain shows signs of preparing for an action before the person becomes consciously aware of deciding. For example, when subjects were told to flex their finger at a moment of their choosing, brain scans revealed a readiness potential several hundred milliseconds before they reported making the decision. The brain moves first. The mind catches up. This raises unsettling questions. If decisions are initiated unconsciously, what role does consciousness actually play? Are we merely observing our choices after the fact, rationalizing what the brain has already decided? Is the feeling of free will just a comforting illusion, like the sensation of control when the car is actually driving itself? Not everyone agrees. Some argue that the readiness potential doesn't reflect a committed decision, just a general state of preparation. Others say that conscious intention still has influence, perhaps in vetoing or shaping unconscious impulses. These debates are ongoing, and the truth is complex, but the findings do suggest that our sense of control may be more fragile than we believe. Philosophers divide the debate into several positions. Hard determinists claim that free will is an illusion. We are entirely shaped by causes beyond our control. Libertarians, in the philosophical sense, insist that we do have free will, and that determinism must therefore be false. Then there are compatibilists, who argue that free will and determinism can coexist. According to this view, being free doesn't mean being uncaused. It means acting in accordance with your desires, without external coercion. Even if your desires have causes, they are still yours. But critics of compatibilism argue that it redefines free will into something else, something smaller. If your desires are shaped by genes, upbringing, and circumstance, are they really your own? If every belief, preference, and reaction can be traced to prior events, then in what sense are you free? You might feel free, but is that enough? Others suggest that free will isn't a binary. It's not something we either have or don't. It may come in degrees, emerging from complexity, self-awareness, and the ability to reflect on our own thoughts. A thermostat reacts to temperature, but isn't free. A human can reflect on motivations, anticipate consequences, and alter behavior. Maybe that's what matters, not absolute freedom, but flexible self-guidance. Still, the philosophical storm persists, because at its core, the free will debate is not just about physics or neurons. It's about meaning, about identity, about justice. If we aren't free, how do we blame? How do we praise? How do we find purpose in a life that unfolds beyond our control? Some thinkers say that the loss of free will is liberating. It allows for compassion. If others are not truly free, we can forgive more easily, understand more deeply. We can shift from blame to curiosity, from punishment to healing. But others fear the opposite, that without free will, society becomes morally hollow. How can there be virtue without choice? How can there be growth, redemption, accountability? The truth may lie somewhere in between. Our choices are influenced profoundly by forces we do not control: genetics, environment, culture, memory, emotion. But within that sea of influence, there may still be a space, narrow but real, for awareness, for reflection, for the ability to pause, to consider, to reshape our trajectory. It may not be total freedom, but it may be enough. Free will might not be a property we possess like an object, but a process we practice, moment by moment, thought by thought. Not an absolute, but a capacity that grows with mindfulness, self-understanding, and care. Perhaps we are not free in the sense of being uncaused, but we may be free in the sense of becoming more than our causes, of choosing not once, but again and again to become something new. Even if determinism is true, there is something remarkable about systems like us that can model themselves, imagine the future, and alter behavior based on imagined outcomes. That kind of recursive self-awareness is rare in the universe. Maybe that's what makes consciousness so strange, and maybe, just maybe, that's where a deeper kind of freedom lies. So what are we left with? A universe of laws and chance, a brain shaped by history and chemistry, a self made of memories and mechanisms. And yet, within that, a spark. The feeling of agency, the moment of pause, the voice that says, I could do otherwise. Is that feeling real? Illusory? Constructed? Science may never answer that fully, but it tells us something even more humbling. That to be human is to live in the tension between fate and freedom, between cause and choice, between what we are and what we strive to be. So the next time you make a decision, big or small, consider this: you are part of a chain of causes stretching back to the beginning of time, but you are also a unique configuration of thought, emotion, and awareness. You are a moment in the story, but you are also its narrator. Whether or not you are free in the absolute sense, you are here, choosing, wondering, becoming. And maybe that's what free will is. Not a power to break the laws of nature, but the ability to shape how we move within them. Not the absence of influence, but the presence of perspective. The ability to pause between impulse and action and say, this is who I will be. The self might be an illusion. You close your eyes, take a deep breath, and feel it, that steady sense of being, a presence behind your thoughts, a self. You assume there is someone there, a continuous eye watching the world, remembering the past, making choices. But when we look closely, scientifically, neurologically, even philosophically, that sense of a singular, enduring self begins to dissolve. Beneath the surface of our experience, the self may be something stranger. Not a thing, but a story. Not a core, but a construction. The self, it turns out, might be an illusion. This idea doesn't mean that you don't exist. It doesn't deny your thoughts, memories, or sensations. But it questions the unified identity you feel behind those thoughts, the feeling that there is one, stable, inner witness that stays constant from moment to moment. Modern neuroscience paints a very different picture. One in which the brain does not house a single you, but is instead a bundle of dynamic processes: perception, memory, emotion, language, each operating in parallel, loosely coordinated, and constantly changing. When scientists peer into the brain, they don't find a central control center. There is no one region where consciousness resides, no throne where the self sits. Instead, they see a network of specialized systems, each handling different functions. Vision is processed in one area, movement in another, language in yet another. These systems communicate, overlap, and influence one another, but they don't converge into a singular, internal CEO. The feeling that there is one may simply be the brain stitching together a narrative after the fact, a kind of internal storytelling that creates coherence from chaos. Split brain studies reveal just how fragmented the mind truly is. In patients whose corpus callosum has been severed, a treatment once used for severe epilepsy, each hemisphere of the brain operates more independently. When stimuli are presented separately to each half, the two sides can generate conflicting responses. One hand buttons a shirt, the other unbuttons it. One hemisphere sees an object, the other has no idea it's there. And yet, the person still feels like a single, unified self. Even when the mind is divided, the illusion of unity persists. The brain seems to work like a federation, not a monarchy, different modules handling different tasks, coordinated but not commanded. And the self, the I that feels like the center of it all, may simply be the product of these modules talking to one another, generating a continuous stream of thought, stitched together like a film reel. The narrator in your mind is not the source of the story. It's a commentary, written in real time, trying to make sense of what's already happening. Even memory, the cornerstone of our identity, is not fixed. It is malleable, unreliable, reconstructed each time we recall it. Our sense of a continuous self across time is built on selective snapshots, edited, reordered, often imagined. Studies show how easily memories can be implanted, distorted, or erased, yet we cling to them as if they form a stable autobiography. In truth, they are more like highlights, fragments curated into a narrative that makes us feel consistent, even when we are constantly changing. Moment to moment, our emotional states shift. Our values evolve. Our personalities adapt. The person you were 10 years ago, or even 10 minutes ago, is not quite the same as the person you are now. Yet the self persists, like a flame that appears stable while its fuel constantly changes. This sense of sameness through change is comforting, but it may be a mental shortcut, a way to reduce complexity and create continuity in an ever-changing inner world. Buddhist philosophy has long recognized this illusion. In teachings over 2,000 years old, it's argued that the self is a collection of aggregates: body, sensation, perception, mental formations, and consciousness, all impermanent, all without a fixed core. There is no self behind the experience, only the experience itself. Clinging to the idea of a permanent self, these teachings say, is the root of suffering, and letting go of that illusion can lead to liberation. Modern psychology echoes this view. The self may be a useful fiction, an emergent property that helps us navigate social life, plan for the future, and interpret our past. It gives us identity, purpose, and continuity. But it may not point to anything concrete inside us. Instead of being a thing, the self is a process, an ongoing performance created by the brain and shaped by experience. Even the moment-to-moment experience of consciousness, the feeling that there is a you who is having the experience, is hard to pin down. When you look for the self in direct experience, it vanishes. You find thoughts, sensations, memories, emotions, but not the thinker, not the feeler. The self seems to hover just out of reach, always implied, never observed. It's like the eye that sees but cannot see itself. Yet despite this, the illusion is incredibly convincing. And perhaps that's for good reason. The belief in a self helps organize behavior, maintain stability, and create personal identity. It makes relationships possible, society intelligible. It gives us a center to return to, even when everything else changes. The illusion has function. It helps us survive. But seeing the illusion for what it is can also be freeing. If the self is not a fixed entity, then we are not trapped by it. We are not bound by our past, not confined by our identity. We can change, adapt, evolve. If the self is a process, then it can be shaped with intention. And if no one part of the brain is in charge, then perhaps we are more collaborative than we know, each moment a negotiation between parts of ourselves. This doesn't mean we don't exist. It means we exist differently than we thought, not as isolated souls or eternal cores, but as patterns of thought, loops of awareness, centers of narrative gravity. We are not the puppet masters of our minds, but neither are we puppets. We are participants in a complex dance of consciousness, fluid, dynamic, and ever-changing. So what are you really? A body? A mind? A name? A story? Maybe all of these, maybe none. Maybe something deeper, a kind of open space where experience happens, a field of awareness in which thoughts arise and dissolve. The self, then, is not the content of experience, but the stage upon which it plays, not the actor, but the spotlight. And when you let go of the idea of a fixed self, when you stop searching for the ghost in the machine, you may find something unexpected: stillness, presence, a deeper kind of freedom, one not tied to identity but to awareness itself. The self might be an illusion, but what remains when the illusion is seen is not empty. It is full, silent, alive. Reality might be a hologram. You reach out and touch the world, a wall, a cup, the skin of your hand. Everything feels real, solid, and three-dimensional. Space seems to extend in all directions, up and down, forward and back, left and right. But what if this perception is misleading? What if the depth you experience is not a property of reality itself, but a kind of illusion, a projection? According to one of the most mind-bending ideas in theoretical physics, known as the holographic principle, the entire universe may be a three-dimensional shadow cast from a two-dimensional surface. In other words, reality might be a hologram. The idea sounds absurd at first. We're used to thinking of holograms as optical tricks, two-dimensional images that appear to have depth. They shimmer and shift, but they're not truly solid. You can't touch them. But the physics version of a hologram is more than a clever image. It's a mathematical framework, a radical rethinking of what space and matter really are. And it began with black holes. Black holes are not just gravitational monsters, they're information paradoxes. According to Einstein's theory of general relativity, black holes form when matter collapses under its own gravity, creating a region from which nothing, not even light, can escape. But in the 1970s, physicist Jacob Bekenstein made a curious observation. The entropy of a black hole, which measures its hidden information, seemed to be proportional not to its volume as you'd expect, but to the surface area of its event horizon. Stephen Hawking expanded on this, discovering that black holes emit radiation due to quantum effects, what we now call Hawking radiation. This meant that black holes could eventually evaporate. But that led to a troubling question. If a black hole disappears, what happens to the information it contained? Quantum mechanics says information can't be destroyed, but general relativity seemed to suggest otherwise. This tension between gravity and quantum theory became one of the deepest puzzles in physics. It was in searching for an answer that the holographic principle was born. In the 1990s, physicists Gerard T. Houft and Leonard Susskind proposed that the information inside a volume of space, say the contents of a black hole, could actually be described by data encoded on its boundary surface. In essence, everything inside the black hole might be a projection from its horizon. This would preserve information and resolve the paradox. But it also suggested something far more profound, that this might not apply only to black holes. What if the entire universe works this way? In 1997, physicist Juan Maltesina proposed a powerful realization of this idea through what's now called the ATS-CFT correspondence. He showed that a certain kind of gravity in a five-dimensional space, known as anti-de Sitter space, is equivalent to a quantum field theory without gravity on its four-dimensional boundary. In other words, the physics of a bulk space can be fully described by the physics on its edge. A higher dimensional world is mathematically identical to a lower dimensional theory. The hologram is not a metaphor, it's a duality. Our universe is not an exact match for anti-de Sitter space, but the implications are staggering. If gravity in space can emerge from quantum interactions on a lower dimensional surface, then what we think of as reality, depth, position, motion, might be emergent, not fundamental. The 3D universe you see and feel could be like the interior of a hologram, projected from data stored on a distant boundary. But where is that boundary? In this theory, it may not be a physical wall somewhere in space, but a conceptual surface at the edge of the universe, possibly the cosmological horizon defined by the limits of what we can observe. Or it could be that all space is encoded in this way, like a cosmic hard drive storing reality not in volume but on area. Every moment you live through could be written on a surface you'll never see. This idea is not science fiction. It's being actively studied, debated, and applied to problems in quantum gravity, black hole physics, and the nature of space-time itself. Some physicists believe the holographic principle may be a key to unifying general relativity with quantum mechanics, a bridge between the large and the small. It offers a new way to think about information, entanglement, and even time. It also invites deep philosophical questions. If what we perceive as 3D is actually encoded in 2D, then what is perception? What is experience? Could consciousness itself be part of the projection, emerging from relationships in this lower dimensional code? Are we, in a very literal sense, characters inside a holographic film, real to ourselves, but arising from something fundamentally different? It's important to understand what the holographic principle does not mean. It doesn't say the world is fake or that we live in a simulation in the science fiction sense. The physics is real. The phenomena are real. What it challenges is our assumption that depth and volume are fundamental. They may be emergent properties like temperature, which arises from microscopic motion, even though no single particle has temperature. Similarly, space may arise from the entanglement of quantum bits on a boundary surface. Reality may be built from information, not objects. This isn't just theoretical musing. In recent years, physicists have discovered that the geometry of space-time, its shape and structure, may be directly related to quantum entanglement. Entangled particles behave as if they're linked, no matter the distance. Some researchers now propose that entanglement is not just a feature of quantum systems, but the glue that holds space-time together. In this view, space isn't a stage where things happen. It's a tapestry woven from threads of information. The holographic principle also dovetails with ideas from string theory, where the basic constituents of reality are not point particles, but tiny vibrating strings. These strings behave differently depending on the number of dimensions they move through. In many formulations, the mathematics works out more elegantly when dimensions are reduced or reinterpreted. Again and again, we see hints that the world we perceive may not be the final layer. So what does this mean for you, for the person listening right now, sitting in a room, feeling grounded in space? It means that your sense of space, solidity, distance, all may be emergent. What feels like the inside of reality could be a decoding of patterns on a more fundamental surface. Your thoughts, your body, your breath, still real, still meaningful, but possibly not located where you believe them to be. Not in 3D, but translated from a realm where geometry itself is a derivative concept. This doesn't negate your experience. It deepens it. It opens the door to a more layered understanding of what it means to exist. You are not less real in a holographic universe. You are more mysterious, more intricate, a living interface between what is and what appears. A being moving through a projection so convincing it becomes indistinguishable from the thing itself. In time, science may confirm or refute the holographic model of reality. It may reveal a new framework altogether, one that makes even this idea seem simple. But for now, the holographic principle invites us to see reality with fresh eyes, not as flat or fake, but as encoded, structured, layered. What you call space may be the tip of a mathematical iceberg. What you call real may be information dancing in dimensions you cannot touch. So the next time you look around, at your room, the sky, your reflection in a mirror, remember this: what you see may be a projection, a decoding of a deeper order, a shadow cast by an unseen surface, not illusion but revelation, not less real but more profound. Reality might be a hologram, and if it is, it means you are part of something even stranger than you thought, not a body in space, but a mind arising from the edge of the infinite, parallel universes, the multiverse. You look around and see a world that feels complete. One sky, one earth, one universe. Everything you know, every person, memory, star, and atom exists within this cosmic bubble we call reality. But what if this universe isn't alone? What if it's just one thread in a much larger tapestry, one bubble in an endless cosmic foam? According to several leading theories in modern physics, this is not only possible, it may be inevitable. Our universe might be just one of countless others in a vast and strange multiverse. The idea of parallel universes has been around for decades, often appearing in science fiction as alternate timelines or mirror realities. But in recent years, physicists have begun to take the multiverse seriously, not as a fantasy, but as a logical consequence of deep theoretical models. These models differ in their details, but they share a haunting implication. The universe you see is only a small piece of a far bigger picture. One path to the multiverse begins with quantum mechanics, the bizarre and counterintuitive framework that governs the behavior of particles at the smallest scales. In the quantum world, particles don't have definite properties until they are measured. Instead, they exist in superpositions, a cloud of possibilities. When a measurement occurs, the wave function collapses, and one outcome becomes real. But what if all outcomes do happen, just in different branches of reality? This is the idea behind the many worlds interpretation. Proposed by physicist Hugh Everett in the 1950s, it suggests that every time a quantum decision is made, every time a particle takes one path or another, the universe splits. One version of reality for each possibility. When you flip a coin, you see heads, but in another universe, you see tails. When you choose left, another you choose is right. The universe constantly branches, endlessly dividing, creating a tree of possibilities as vast and intricate as imagination itself. According to this view, the multiverse isn't out there, it's here. You are surrounded by parallel versions of yourself, living out every choice you didn't make, every path you didn't follow. These alternate realities don't interact, but they exist. All equally real, all equally valid. The world you experience is just one slice of a cosmic superposition, one thread in an infinite weave. But the quantum multiverse is only one possibility. Another comes from cosmology and the theory of eternal inflation. In the early moments of the Big Bang, the universe underwent a rapid expansion, an inflationary burst that stretched space at unimaginable speed. According to inflation theory, this expansion didn't stop everywhere at once. Some regions of space stopped inflating and formed bubble universes like ours, while others kept expanding. This process may still be happening, endlessly, creating new universes in distant regions, each isolated, each potentially with its own laws of physics. This leads to a bubble multiverse, where our universe is just one among many, each bubble a separate cosmos, born from the same underlying field but unfolding with its own rules. Some bubbles may have more dimensions. Some may have different particles. Some may collapse in a flash, while others evolve stars and galaxies. We cannot reach these other bubbles. The space between them is expanding too quickly, but their existence may still leave subtle fingerprints, tiny imprints in the cosmic microwave background or delicate patterns in the distribution of galaxies. Then there's the idea from string theory, which proposes that the fundamental building blocks of the universe are not particles, but vibrating strings. In string theory, there are many ways to compactify the extra dimensions that the theory requires. Each compactification leads to a different set of physical laws. This vast landscape of solutions gives rise to a string theory multiverse, a nearly infinite menu of realities, each with different constants, particles, and forces. In this view, the universe you inhabit is not the only way things could be. It's just the version compatible with your existence. This idea is sometimes linked to the anthropic principle. We find ourselves in a universe with the right conditions for life because we couldn't exist in one that wasn't. Most universes might be sterile, lifeless, chaotic, but somewhere among the infinity one has stars, carbon, consciousness, and you. It's a humbling thought that our universe, so vast, so ancient, might be ordinary, that what we see is not the whole of reality, but a tiny, habitable niche in a cosmic ocean. And that far beyond our reach, there may be other universes, some eerily similar, others wildly alien, realms where time runs backward, or where light travels differently, worlds where Earth never formed, or where you were never born. But how can we ever know? If these other universes are forever beyond our horizon, are they just speculation? Is the multiverse science or philosophy? This question divides physicists. Some argue that if a theory predicts a multiverse as a consequence, and that theory is otherwise testable and successful, then we should take the multiverse seriously. Others caution against accepting ideas that can never be directly observed. The debate is ongoing, yet evidence may come indirectly. Some versions of inflation predict patterns in the cosmic microwave background, subtle imprints that could hint at collisions with other bubbles. Quantum experiments may one day test the predictions of many worlds versus other interpretations, and string theory, still incomplete, may reveal deeper structures that support a multiversal view. Beyond physics, the multiverse raises profound philosophical and existential questions. If there are infinite versions of you, does that diminish your uniqueness? If every possible choice is played out somewhere, does free will still matter? Some find comfort in the idea that no opportunity is ever truly lost. Others feel unease, wondering what it means to be you in a sea of selves. But perhaps the multiverse doesn't make you smaller, it makes the cosmos richer. You are still the only version of you in this world. Your experiences, your choices, your relationships, they are real, meaningful, and singular. You are one branch of possibility, one thread in the grand design, and that makes your path no less important. It may even make it more so. Because even if other worlds exist, even if countless realities bloom beyond our own, this one is the only one you live in. This is the reality that holds your breath, your memories, your moments. The multiverse may expand the borders of the real, but your life still unfolds here, in this shimmering universe, under this singular sky. So the next time you look up at the stars, remember what you see may be just one bubble in an endless cosmic sea, a universe among universes, a whisper in the eternal hum. And while we may never visit those parallel worlds, their possibility invites awe. It reminds us that reality is deeper than we can imagine, that the cosmos is not a single book, but a library, and that somewhere, always, another story is beginning. Boltzmann brains. You trust your memories. You believe the world around you has a history, that the stars were born billions of years ago, that the earth formed from dust and fire, that you lived a childhood, made choices, became who you are. But what if none of that is real? What if everything you know, your memories, your body, this moment, came into existence a few seconds ago, fully formed, as a brief fluctuation in an indifferent void? This is the unsettling question posed by one of the strangest thought experiments in physics, the Boltzmann brain. The idea begins with the 19th century physicist Ludwig Boltzmann, who tried to explain the low entropy state of the universe. Entropy, the measure of disorder, tends to increase over time. Yet our universe began in a state of remarkable order. Why? Boltzmann suggested that in an eternal universe governed by statistical mechanics, rare fluctuations could produce temporary pockets of order. Most of the time, the cosmos would be in thermodynamic equilibrium, maximum entropy, maximum chaos. But given enough time, even extremely improbable events can occur. And one such event might be the spontaneous emergence of a region like our observable universe. But this reasoning leads to a paradox. If we live in an infinitely old or infinite universe, one that endures forever and allows every possible fluctuation, then statistically, it's far more likely for a small fluctuation to occur than a large one. Creating a full, structured universe like ours would require a massive, coherent drop in entropy. But creating a single conscious brain, floating in a sea of randomness, would be far easier. No stars, no galaxies, just a brain, formed by pure chance, fully aware, complete with memories, and the illusion of a coherent past. This hypothetical entity is known as a Boltzmann brain, a self-aware fluctuation in the fabric of chaos, a brain that thinks it lived a life, remembers a childhood, perhaps even believes it's listening to this very narration. But none of those memories are real. There is no past, no future, just a moment of thought, followed by silence. The logic is deeply disturbing. If such brains are far more probable than entire low-entropy universes, then shouldn't we expect to be one? Shouldn't the typical observer in a fluctuating cosmos be a Boltzmann brain? After all, it takes less energy, less order, less coordination to create a single brain than to evolve billions of galaxies. If the universe is eternal and random at its core, then these momentary minds would vastly outnumber beings like us, beings who arose through billions of years of evolution, structure, and coherent physical law. But if that's true, if you are a Boltzmann brain, then everything you believe is suspect. Your memories are false. The world around you doesn't exist. There is no yesterday, no tomorrow, just a fleeting moment of thought in an otherwise meaningless sea. The paradox collapses trust in reason, science, and experience. Because if you can't rely on memory, on cause and effect, then no belief is safe. Most physicists recoil from this conclusion. It feels wrong, philosophically, emotionally, and scientifically. But the disturbing power of the Boltzmann brain is that it arises from seemingly logical premises. It forces us to confront the deep assumptions behind our cosmology. It asks, what kind of universe produces minds like ours, and what makes us typical, or atypical, among all possible observers? To avoid the paradox, modern cosmology has moved away from Boltzmann's model of an eternal, static universe. The discovery of cosmic expansion, dark energy, and the Big Bang suggests that our universe is not infinitely old. It had a beginning, and it is evolving. If the universe is finite in age or governed by mechanisms that prevent runaway fluctuations, then Boltzmann brains may never form. Some cosmological models include a built-in cutoff, such as cosmic horizons, vacuum decay, or heat death, that effectively limit the time available for random brains to appear. Moreover, most cosmologists argue that any theory that predicts Boltzmann brains to vastly outnumber ordinary observers is inherently flawed. If your theory says you're most likely a brain in a void, despite all evidence to the contrary, then it undermines itself. It becomes self-defeating. Reliable reasoning requires a stable framework, and a Boltzmann brain has none. It only believes it does. This principle has become a kind of filter in theoretical physics. If your model of the universe implies that typical observers are Boltzmann brains, then your model is probably wrong. It's a sanity check, a way to rule out universes that are too random, too infinite, too permissive. It doesn't solve the mystery, but it narrows the possibilities. Some suggest the paradox teaches us something deeper, that consciousness cannot be fully explained by structure alone, that subjective experience may require more than a brain-shaped blob of atoms. Perhaps memory is not enough. Perhaps meaning depends on embeddedness in a real, unfolding world. If so, then Boltzmann brains may look like minds, but lack the grounding that makes awareness truly coherent. Still, the idea haunts modern cosmology. It looms at the edge of theories about entropy, heat death, eternal inflation, and the nature of time. It whispers that probability is not always intuitive, that the universe may allow for minds without worlds, and that we must be careful when defining what exists. It also challenges our notion of typicality, of what it means to be a normal observer. Are we rare or common? Are we the product of physical law, or the consequence of random chance? These questions strike at the heart of cosmology, philosophy, and even the nature of identity. If you are not a Boltzmann brain, if your memories are real, your past consistent, your world continuous, then that fact tells us something important about the universe. It suggests that we live in a cosmos where observers like us are natural, where structure, time, and evolution are part of a real, ongoing story, and that story has shape, coherence, meaning. But the Boltzmann brain remains a reminder, a thought experiment, not to convince you that your life is false, but to show how strange the universe must be to make your life real. It pushes us to ask better questions, to refine our models, to understand the deep connection between entropy, time, consciousness, and the very definition of existence. So the next time you find yourself staring into the night sky, wondering about the stars and your place beneath them, remember this: your memories feel real because they are supported by an entire universe, rich, structured, ancient. You are not a flicker in the void. You are the product of cosmic history, not a spontaneous mistake. And the very improbability of the Boltzmann brain helps confirm the wonder of what you actually are. You are not a brain in chaos. You are a mind in motion, woven from time, shaped by cause, grounded in a universe still unfolding. The simulation hypothesis. You wake up in your room, stretch your limbs, look out at the world, and everything feels normal. The ground beneath your feet is solid. The sky above you appears real. Your memories line up in sequence, and your thoughts seem like your own. But what if none of this is what it seems? What if the world around you, the stars, the oceans, even your own body, is not fundamentally made of matter, but of information? What if you're not living in a universe at all, but inside a sophisticated simulation? This is the unsettling suggestion of the simulation hypothesis, an idea that has moved from science fiction into the realm of serious philosophical and scientific debate. It proposes that the entire universe we inhabit might be an artificial construct, a virtual reality generated by an unimaginably advanced intelligence. And if that's true, then everything we think we know about time, space, life, even consciousness, may be part of a program running somewhere else. The modern version of the hypothesis is often traced to philosopher Nick Bostrom, who in 2003 laid out a provocative argument. He suggested that at least one of the following three statements must be true. First, that most civilizations at our level of development go extinct before becoming technologically mature. Second, that advanced civilizations, for some reason, choose not to run ancestor simulations of minds like ours. Or third, that we are almost certainly living inside such a simulation. It's a logic trap. If future civilizations develop the power to simulate conscious beings, and they run many such simulations, then the number of simulated minds would vastly outnumber real ones. So statistically, it's far more likely that you're one of the simulated minds, a digital consciousness, a self-aware process running on someone else's machine. You might wonder, how could a simulation be that detailed? Wouldn't it be obvious? But consider how quickly our own technologies are evolving. A few decades ago, digital worlds were pixelated and crude. Today, video games are immersive and nearly photorealistic. Now imagine a future civilization with millions of years of advancement behind them, with quantum computers, brain emulation, and AI systems indistinguishable from thought itself. For such a civilization, simulating entire worlds, down to every atom, every neuron, every memory, could be trivial. And you wouldn't need to simulate the entire universe at once, just the part observed by the conscious agent. Like a game rendering only what the player sees, the simulation could fill in details as needed. The stars in the sky, the people on the street, even the cells in your body called into being only when and if you look. From the inside, it would feel seamless, real, undeniable. But what evidence is there? Physicists and philosophers have searched for hints. Some wonder if the universe's discreteness, the way energy and matter come in quantized units, could be a sign of an underlying grid, like pixels on a screen. Others point to the mathematical nature of physical laws. Why is reality governed by equations? Why is it computable at all? Some even look for glitches, anomalies in the constants of physics, or unexplained patterns in cosmic radiation as possible signs of the simulation's operating limits. None of this is conclusive, but the deeper we look into reality, the more it begins to resemble a codebase. The laws of physics, the constants of nature, the structure of particles, all follow a kind of logic. And logic, after all, is what computers run on. Still, many scientists are skeptical. They argue that the simulation hypothesis is unfalsifiable. That is, there's no experiment that could definitively prove or disprove it. If the simulation is perfect, how could we ever tell? And if we can't test it, is it science? Or just modern metaphysics in digital clothing? Some respond that this is beside the point, that the simulation hypothesis, like earlier questions about reality, is meant to provoke deeper inquiry. Like Descartes wondering if a demon was deceiving him, or Plato describing a cave of shadows, the hypothesis forces us to ask, how do we know what's real? It also invites fascinating ethical and existential questions. If we're in a simulation, who built it? Why? Are we entertainment? Research? Art? A school project? A curiosity running in a lab that's long been abandoned? And if there are simulators, do they watch us? Intervene? Or are we completely on our own, looping through an artificial world, unaware of the boundaries? Then there's the question of consciousness. If simulated beings like us can think, feel, suffer, and wonder, then consciousness must not depend on biology. It must be substrate independent, a process that can run on meat or silicon, on neurons or code. This view, sometimes called computationalism, holds that minds are not matter-bound, they are patterns, and if true, it expands the possible homes of consciousness across galaxies, hard drives, and beyond. But what does it mean to be you in such a world? If your memories were uploaded, if your choices were coded, if your mind were emulated, would you still be real? Or would you be a copy of a copy? A line of logic repeating itself in digital silence. The simulation hypothesis doesn't answer these questions, but it asks them with intensity, and in doing so, it reshapes how we think about the self, identity, and the nature of being. It also opens a door to humility. If we are inside a simulation, then we are not at the top of the intellectual ladder. We are not the architects, we are the simulated. What we call the universe might be one of many, a small, virtual room inside a vast stack of realities. Our gods might be coders, our laws of nature, adjustable settings, our lives, data. Some find this terrifying. Others find it liberating. Because if the world is simulation, then it's not fixed. It's designed. And what is designed can be understood, perhaps even influenced. In a simulated universe, meaning is not lost, it's layered. And truth becomes a matter of decoding. Still, many scientists remind us, even if we're not in a simulation, the world is no less mysterious. The universe itself, whether simulated or not, is governed by deep, intricate rules. It gave rise to life, thought, and self-awareness. That in itself is a miracle, whether it's running on hardware or not. So what should we do with this idea? Should we fear it? Pursue it? Treat it as a curiosity? Perhaps, like all profound thought experiments, the simulation hypothesis is not meant to be solved but felt. It holds up a mirror to our assumptions. It blurs the line between real and rendered. It reminds us that certainty is always partial, that behind every answer lies a deeper question. And maybe that's the point. Whether we live in base reality or a clever simulation, our thoughts are still ours. Our emotions still matter. Our relationships still shape us. Even a simulated world contains real pain, real joy, real beauty. If the simulation is good enough to feel real, then maybe that's real enough. So as you walk through your day, listening to voices, touching objects, remembering your past, pause for a moment. Consider the strange possibility that you are part of a digital dream, that everything around you, even your thoughts, arise from code, and then let that thought go. Because simulated or not, this moment is yours. This breath is yours. This awareness is real. You may be in a simulation. You may not. But either way, you are here, thinking, wondering, awake in the mystery, the unreasonable effectiveness of mathematics. You sit with a pencil in hand, drawing lines on a blank page. You create shapes, angles, and symbols. A triangle, a circle, a simple equation. What starts as marks on paper begins to resemble a pattern, then a principle, then a law of the universe. And suddenly, you realize that the abstract language you're scribbling somehow describes the orbits of planets, the behavior of atoms, even the birth of stars. Mathematics, in all its purity and precision, somehow maps onto reality. And that is astonishing. This strange connection has baffled philosophers and physicists alike. Why should numbers, products of human thought, so perfectly describe the physical world? Why should imaginary constructs like negative numbers, complex equations, and abstract topologies correspond so precisely to things that exist? This mystery was famously described by physicist Eugene Wigner, who called it the unreasonable effectiveness of mathematics and the natural sciences. He wasn't exaggerating. He was expressing a wonder that still lingers at the heart of modern science. Consider this. Equations devised without reference to the real world later turn out to describe it. Mathematicians exploring strange, abstract systems, purely for curiosity, find their work decades later at the core of quantum theory or relativity. The complex numbers, once considered just a playful trick of algebra, now govern the behavior of particles. Non-Euclidean geometry, once seen as a mathematical curiosity, became the foundation of Einstein's general theory of relativity. These are not isolated cases. This happens again and again. Why should the universe be written in the language of math? When we study physics, we find that reality behaves as if it's obeying mathematical rules. Equations that not only describe but predict events with shocking accuracy. Newton's laws of motion, written in elegant calculus, predicted the paths of celestial bodies centuries before we could verify them. Maxwell's equations predicted radio waves before anyone had built a transmitter. Schrödinger's equation, etched in symbols, tells us where electrons might be in their cloud-like uncertainty. It's as if math is not just a tool, but the fabric. As if nature does not just follow math, but is math. And here, a question opens like a quiet chasm. Is mathematics invented or discovered? If math is invented, then it is the product of the human mind, like chess or language. We created it to organize our thoughts, to measure, to build. Under this view, math is a model, not a mirror, a map, not the terrain. But if this is true, why does it work so well on the terrain? Why do equations invented on chalkboards end up predicting the movement of galaxies? On the other hand, if math is discovered, if it exists independently of us, then it must be a part of the universe's deep structure. We don't make math, we uncover it, like archaeologists brushing dust off ancient bones. We tap into something timeless, something real, something that was always there, long before minds evolved to count or measure. But even this answer raises questions. If math is real, where does it live? Not in space, not in time. The number 2 exists, in some sense, but not as a thing you can touch. It exists in a realm outside physicality. Some philosophers, like Platonists, argue that mathematical truths reside in a non-physical, timeless realm, that numbers, shapes, and formulas exist like eternal forms, and we glimpse them through intuition and logic. Yet others push back. They argue that math is a language, an extraordinarily useful and precise one, yes, but not a reality in itself. It models the universe because we shaped it to do so. We prune and refine math to match nature's curves and cycles, and we discard the parts that don't fit. Under this view, math works because we made it work. But this explanation also seems unsatisfying, because math often outpaces us. We don't always know what it's for when we invent it. Group theory, developed for the beauty of symmetry, later became crucial in particle physics. Topology, an esoteric branch of geometry, became the language of quantum fields and condensed matter. It's as if math knows more than we do, whispering truths long before we realize what they mean. And so we find ourselves in a curious position, living in a world that behaves like an equation, where objects fall, not randomly, but according to FMA, where energy, mass, and light interrelate through E-2, where the patterns of chaos can be modeled by fractals and the curves of space by tensors. Even the randomness of quantum mechanics unfolds according to strict mathematical rules. It raises the possibility that the universe is a kind of mathematical structure. This is not merely poetic. It's a serious hypothesis entertained by physicists like Max Tegmark, who suggests that all physical reality is ultimately a mathematical object. According to this view, we don't just use math to describe the universe, we live inside it. The equations are reality. But how could we ever know if this is true? Is math pointing to something deeper, or simply reflecting our own minds? Maybe we see the world through mathematical lenses, because we evolved to detect patterns. Our brains are natural pattern finders. Perhaps what we call truth is simply the most efficient approximation for survival. But if so, why would that approximation align so closely with quantum theory, with relativity, with cosmology? Why should a being descended from apes and trees be capable of writing down the laws that govern black holes? Why should we be able to map the shape of the universe with differential geometry, or simulate particles with matrices and spinors? Something about this feels too elegant, too precise, too strange. It leads to one final question. Not just why math works, but what is it pointing to? Maybe mathematics is the shadow cast by something deeper, a hidden code, a structure beneath reality. And maybe that's why it's so unreasonably effective, because the universe is not a chaotic accident, but a system, an ordered, lawful, mysterious system that we only partially understand. When you look at a flower and see the Fibonacci spiral in its petals, when you gaze at the night sky and calculate the orbital resonance of moons, when you study the structure of snowflakes, the symmetry of crystals, the harmony of musical intervals, you are not just seeing beauty, you are seeing order. And order is mathematical. So the next time you solve a simple equation or watch a planet trace its elliptical orbit, pause for a moment. Consider that you may be touching the language of the cosmos. That numbers may not merely describe reality, but constitute it. That your mind, in reaching for mathematical truth, may be echoing the very thoughts of the universe itself. In that quiet moment of understanding, where symbol meets sensation and logic meets beauty, you are no longer just a brain with thoughts. You are part of a pattern. You are an expression of the math that shapes galaxies and governs the fall of light. Whether math is discovered or invented may never be fully answered, but its unreasonable power whispers that the universe is not blind chaos. It is, in some deep and wondrous way, written. Infinity causes problems. Infinity. The word sounds poetic, almost divine. A horizon without end. A number bigger than all others, a concept so vast it defies imagination. Yet beneath its elegant surface lies a problem, because infinity, for all its beauty, breaks things. It twists logic, snaps physics, and leaves us staring into paradox. And the deeper we explore the nature of the universe, the more we realize actual infinity might not just be strange, it might be impossible. Let's begin with mathematics, where infinity first came to life. You can divide numbers forever. 1/2, 1/4, 1/8, and so on. There's no end to how small the pieces get. The number line, too, stretches infinitely in both directions. And yet we can hold all of this in a single equation. Math is where infinity plays freely. But even here, things get weird. Consider Hilbert's Hotel, a thought experiment from the mathematician David Hilbert. Imagine a hotel with an infinite number of rooms, all of them occupied. A traveler arrives. Can he stay? Of course, says the hotel manager. Just shift every guest over one room. Room 1 moves to 2, 2 to 3. and so on. Room 1 is now empty. A second traveler arrives. Then 100. Then 1,000,000,000. Then an infinite number. No problem. Just rearrange everyone using a clever formula, and somehow there's always room. The paradox isn't just that this works, it's that it makes logical sense and yet feels completely absurd. Infinities don't behave like normal numbers. They warp intuition. Now shift from math to physics, and the problems deepen. Our physical theories break when confronted with infinities. Take black holes. At the heart of a black hole lies a singularity, a point of infinite density, infinite curvature of space, infinite gravity. According to Einstein's general relativity, the equations literally divide by zero here. Time and space stop behaving. Physics collapses. But the real world can't support such infinities. A singularity is a sign that something has gone wrong with our model. It's not a place, it's a breakdown, a red flag in the math. We see the same problem at the beginning of the universe. The Big Bang Theory suggests that all matter, energy, space, and time erupted from an initial singularity, a point of infinite density and temperature. But again, this infinity isn't physical. It's the point at which our understanding ends. It tells us our equations don't reach far enough, that we need something deeper, like quantum gravity, to resolve the paradox. Infinity even disturbs quantum mechanics. When early quantum field theories tried to calculate particle interactions, the results came back with infinite energy values. Nonsense. To fix this, physicists invented a mathematical trick called renormalization, which cancels out the infinities by redefining certain quantities. It works, but it feels like patchwork. A workaround, not a solution, and the fact that we need it suggests that something isn't quite right. So what's going on? Is infinity real, or just a tool? Some thinkers argue that actual infinities, as opposed to potential infinities, don't exist. A potential infinity is like counting. You can always count one more, but you'll never actually reach infinity. It's a process, not a thing. Actual infinity, by contrast, would be a completed, boundless quantity, and that's where the trouble starts. Infinity as a limit is useful. Infinity as a thing is dangerous. In cosmology, infinity causes headaches. Is the universe infinite in size? If so, then it must contain infinite matter, infinite stars, infinite versions of you, doing infinite things. Somewhere there's a version of this very moment playing out with just one word different. Somewhere else, everything is identical except you blinked half a second earlier. This isn't science fiction. It's a consequence of infinite space combined with finite matter arrangements, and it leads to paradox. If everything happens infinitely, then meaning gets diluted, probability becomes slippery, uniqueness evaporates. Then there's the measure problem in cosmology. In an infinite universe, how do you compare things? If there are infinitely many red galaxies and infinitely many blue ones, what percentage are red? Infinity divided by infinity is undefined. So how do you assign probabilities? How do you say what's likely or unlikely in a world where everything happens somewhere infinitely? This breaks the foundations of statistical reasoning, and it remains an open problem in physics. Infinity also raises ethical paradoxes. In an infinite multiverse, every possible suffering, every possible joy, plays out endlessly. Does this make individual suffering meaningless? Or infinitely worse? If every tragedy occurs infinitely often, what does that say about morality, choice, and consequence? These are not just abstract puzzles. They touch the very nature of value, purpose, and responsibility in a possibly infinite reality. Some physicists, like Stephen Hawking, argued that the universe avoids actual infinities, that infinities are simply signs of incomplete understanding. Others, like Roger Penrose, embraced the strange consequences of infinite cycles, proposing models like conformal cyclic cosmology, where the universe regenerates endlessly through a series of aeons. Meanwhile, mathematicians like Georg Cantor tried to tame infinity, dividing it into levels, showing that some infinities are larger than others. But even Cantor was haunted by the concept. He once described infinity as a divine mystery, something the human mind cannot fully grasp. And perhaps that's the point. Infinity isn't a number. It's a mirror. When we reach for it, we reveal the limits of thought, the edges of comprehension. In trying to hold it, Our tools falter math, logic, even language. We build systems to contain it, and it slips through the cracks. Yet we need it. We rely on infinity in calculus, in thermodynamics, in signal processing, in nearly every field of physics and engineering. We use it to describe things that go on forever, but always cautiously, always with warning signs. Infinity is the skeleton key of the universe, but it unlocks more questions than answers. And maybe that's why it fascinates us, because it whispers that reality is bigger than we can know, that there are truths beyond reach, that there is no final number, no last idea, no boundary to the quest. In that way, infinity is not just a concept, it's a challenge, a reminder that our models are only maps, that the terrain keeps going forever. So the next time you hear the word infinity, let it settle in your mind, not as a quantity, but as a mystery, a shimmer at the edge of knowledge, a question mark too big to erase. It may break our theories, defy our tools, and dissolve our definitions. But it also invites us to think further, reach deeper, imagine more. Because in a universe where infinity might be real, the only limits are the ones we haven't broken yet. Emergence, when the whole becomes something new. Imagine watching a murmuration of starlings in the evening sky, thousands of birds, sweeping and swirling in a unified dance, forming fluid patterns that seem almost alive in their own right. There's no leader, no blueprint. Each bird is following simple rules. Stay close, match direction, avoid collision. And yet the result is a breathtaking ballet, something more than any single bird could produce. This is emergence. When many small things come together and give rise to something larger, something new, something that doesn't exist in any of the parts alone. At first glance, it seems like a simple idea. But the more you look, the more it unravels everything you thought you knew about complexity, consciousness, and what it means to be real. Emergence is not just a feature of flocks or colonies. It's a fundamental aspect of our world. Life is emergent. Minds are emergent. Storms, markets, ecosystems, all are shaped by emergence. And what makes it so strange is that you can't fully explain the whole by analyzing the pieces. Something novel appears. A pattern, a behavior, a meaning that wasn't there before. Let's begin with something small: cells. Each cell in your body is a tiny biochemical machine. It responds to signals, processes energy, follows genetic instructions. But a single cell is not a person. It doesn't think, feel, or remember. Yet put trillions of these cells together in the right arrangement, and somehow you get a mind, consciousness, a sense of self, memories, emotions. None of these things are stored in any one neuron, or gene, or molecule. They emerge from the interaction of billions of simple units, each obeying local rules and collectively creating something astonishing. This is what emergence reveals, that complexity doesn't have to be built from complexity. It can arise from simplicity. Think of an ant. On its own, it's just an insect following chemical trails. But in a colony, ants become engineers, warriors, farmers. They build nests with chambers and ventilation systems. They organize labor, defend territory, and adapt to changing environments. No ant knows the full plan, but the colony behaves like a single, intelligent organism. This is collective intelligence, a hallmark of emergent systems. The weather is another example. The laws that govern air pressure, temperature, and moisture are simple enough, but from them arises the chaotic dance of wind and rain, the swirling power of hurricanes, the delicate balance of climate. Meteorologists can study the ingredients of a storm, but the storm itself is something more, a system that pulses, moves, evolves, a pattern too complex to fully predict. Even consciousness, the great mystery, may be emergent. The firing of neurons, the transmission of signals, the interplay of sensory inputs and memory recall. None of these are consciousness alone, but taken together, they may give rise to awareness, a subjective experience, the feeling of being. This view challenges reductionism, the idea that everything can be explained by its smallest parts. Emergence suggests that reality has layers, and each layer may have properties the layer below lacks. It's tempting to think of this as just complexity, but emergence isn't just complicated, it's unexpected. The behavior of the whole is not obvious from the rules of the parts. A chessboard has simple rules, but the game's depth is infinite. A computer runs binary code, yet from it emerges language, music, intelligence. These systems are not just large, they are self-organizing. They produce order, structure, meaning from the bottom up. This has profound implications. It means that reality is not just built, it unfolds. Systems evolve not by design, but by interaction. There may be no central controller, no architect, no master plan. Instead, emergence gives us a universe that builds itself through layers of interaction, feedback, and adaptation. In the human world, we see emergence in culture, in economies, in the spread of ideas. No single person invented language. It evolved through interaction, generation after generation. Morality, art, religion, politics, these are emergent phenomena. They grow out of minds engaging with other minds. They are patterns in motion. The crowd is not just many individuals, it is something else. A mood, a force, a behavior no one intended, but everyone participates in. Even science itself is emergent. Theories are built on data, insights build on other insights, and knowledge evolves through debate, discovery, and refinement. No single mind contains the entirety of science, but the network of minds produces understanding. We are, in many ways, part of a larger thinking system, culture as cognition, humanity as one giant learning brain. But emergence also raises questions. If the whole is different from the sum of its parts, what determines its behavior? Is there a tipping point where a system becomes more than its pieces? When does matter become life? When does behavior become thought? When does pattern become mind? These transitions are still poorly understood. They are thresholds, bridges between levels of reality. And then there's the question of control. If consciousness is emergent, then who or what is in charge? If we are patterns made of patterns, can we steer the systems we are part of? Or are we just passengers in an emergent flow? The answer may lie somewhere in between. Emergence is not deterministic in the strict sense. It allows for feedback, for loops, for self-reference. It gives rise to systems that can reflect on themselves, adapt themselves, even design new emergent layers. This is where the mystery deepens. Because emergence is not just a feature of living systems, it may be fundamental to the universe itself. The cosmos starts with basic laws: gravity, electromagnetism, quantum rules. From these, stars and galaxies emerge. From stars come planets. From planets, chemistry. From chemistry, biology. And from biology, minds. It's a cascade of emergence, a hierarchy of being. Each level gives rise to new possibilities. The universe is not static, it unfolds in layers. And maybe that's the ultimate insight. That reality is not made of things, but of relationships. Not particles, but processes. Emergence teaches us that what matters is not just what exists, but how it interacts. Life is not in the cell, but in the way cells work together. Mind is not in the neuron, but in the way neurons dance. Order is not imposed from above. It arises from the dance of parts, the murmuration of complexity, the whisper of many into one. So next time you look at a cloud forming in the sky, or a city bustling with life, or a child learning to speak, pause and consider what you're witnessing. You are watching emergence, the universe making something new out of what already was, the miracle of higher order, born from lower chaos. And in that moment, you may sense something deep, something sacred, that you too are an emergent pattern, that your thoughts, your dreams, your very self, are the echoes of complexity woven through time. And perhaps that's all we are. And perhaps that's more than enough. Your senses lie radically. You wake each morning into what feels like reality. Light pours through the window. The world hums with sound, shape, color, and motion. You hear your name, see your hand, feel the sheets beneath you. It all seems so direct, so real. But the truth is stranger and far more unsettling. What you experience isn't reality itself. It's a model, a constructed simulation running in your mind. Your senses are not windows to the world. They are filters, narrow, distorted, and radically selective. We live inside a sliver of existence. Consider light. The electromagnetic spectrum stretches from radio waves as large as mountains to gamma rays smaller than atoms. But your eyes see only a thin band, a narrow rainbow between infrared and ultraviolet, less than 1/1,000,000th of the full spectrum. To you, this is color, but it's an illusion of omission. Bees see ultraviolet patterns on flowers invisible to us. Snakes detect infrared heat signatures glowing from prey. Birds perceive magnetic fields like invisible maps in the sky. And humans? We live in a dim shadow of what's truly there. Sound is no different. You hear vibrations between about 20 and 20,000 hertz. That's it. Below this range, whales sing in deep rumbling tones across oceans, while above it, bats navigate entire worlds through ultrasonic cries. These experiences are utterly real to them, but forever sealed off from your awareness. Your sense of hearing, so rich, so nuanced, is still just a thin slice of what's possible. You don't hear most of what's happening around you. You never will. Touch, too, is deceiving. You feel solidity, firmness, weight, texture, but matter is mostly empty space. Atoms are vast voids, with tiny nuclei surrounded by whirling electron clouds. When you press your hand against a table, you're not touching it in the way you think. What you feel is the repulsion of electromagnetic forces, your electrons pushing against the table's electrons. Nothing solid ever really meets. You never truly touch anything. Even your sense of time is misleading. You experience it as a smooth, linear flow from past through present to future. But physics disagrees. At the quantum level, time doesn't behave this way. Events blur and smear into probabilities. In Einstein's relativity, simultaneity vanishes. What's now for you may be future or past for someone else, depending on their speed. There is no universal present. The ticking of your mental clock is not a property of the universe. It is a story your brain tells to make sense of change. And that brain, for all its power, doesn't show you the world. It constructs one. Your eyes don't see objects, they detect light bouncing off surfaces. Your ears don't hear sounds, they measure changes in air pressure. Your skin doesn't feel objects, it senses vibrations and force. The brain takes these raw signals and weaves them into experience. But it edits. It filters. It fills in gaps. You don't see with your eyes, you see with your brain. And your brain sees what it expects to see. Visual illusions reveal the cracks in this system. A static image seems to move. Two lines of equal length look different. A flat drawing becomes a cube, a face, a tunnel. These aren't glitches. They're features. Your brain is optimizing for speed, not truth. It's trying to build a coherent story fast enough to keep you alive. Accuracy is secondary. That's why your peripheral vision is blurry and colorless. Your brain fills it in. That's why you can't see your blind spot. Your brain hides it. You are not perceiving reality. You are hallucinating, usefully, consistently, but hallucinating nonetheless. The philosopher Immanuel Kant called this the phenomenal world, the world as it appears to us. He believed there was also the noumenal world, reality as it is in itself, forever hidden. We can never access it directly. Only through the interface of perception, through the veil of our senses. More recently, cognitive scientists like Donald Hoffman suggest that evolution has shaped perception not for truth, but for survival. We don't see reality. We see a user interface, a simplified dashboard, like icons on a screen. You don't see the circuitry in your computer. You see folders, files, and trash bins. That's not what's really there. It's what helps you function. So too with reality. But this interface is not universal. Other creatures live in radically different worlds. To a bat, reality is sonar. To a dog, it is scent. To a jellyfish, it is pressure and chemical gradients. Each species perceives a unique slice of existence. We call this Umwelt, the perceptual world of an organism. And your Umwelt is as limited as any other. The reality you experience is not the reality. It is a version, tailored by biology, culture, memory, and mind. Even within your own mind, perception is unstable. Close your eyes and remember a face. The image appears, detailed yet fluid. That's your brain reconstructing from fragments. Now think of a dream. In dreams you see, hear, touch, but none of it is real. The same machinery that creates waking perception creates dreams. There's no special system for fantasy. It's all the same process, which means in a very real sense, waking life is a controlled hallucination, your brain generating reality from prediction, memory, and minimal input. This doesn't mean nothing is real. It means you never experience it directly. Reality is mediated, translated, processed, filtered through nerves, coded into patterns, interpreted by circuits. What you get is a simulation. A good one, yes. Often reliable, but still a simulation. This insight is humbling. It means we cannot trust our senses to tell us the full story. It means we must be cautious about certainty, about what we see, hear, feel. It invites us to expand our tools, to peer beyond biology with microscopes, telescopes, sensors, and algorithms, to listen for the inaudible, to image the invisible, to discover worlds within worlds. But it also opens a door inward. If perception is constructed, then it can be altered, expanded, refined. Through meditation, through psychedelics, through neuroplasticity. Mystics have long spoken of transcending ordinary perception, seeing unity, energy, pattern. Science now begins to glimpse the same. Brain scans show that altered states change how sensory information is integrated. They quiet the default mode network, the system that builds your sense of self, and reveals something more fluid, more connected, more emergent. So perhaps the limitations of your senses are not just a boundary, but a gateway, a challenge to reach beyond, a reminder that truth is larger than what appears, that the world is richer than your interface, that your experience is just one layer of the great tapestry. And when you sit quietly and feel the breath moving in and out, and hear the subtle sounds around you, and realize that all of it, all sensation, is happening inside your awareness, you glimpse the strange truth at the heart of being, that reality is not out there, waiting to be seen. It is co-created by the world, by your senses, and by the mystery of consciousness itself. You are not a passive observer. You are a participant in a dance between mind and matter. Your senses do not lie maliciously. They lie creatively, constructing a useful dream, a functional fiction, a coherent now. And that fiction, though incomplete, is enough. Enough to live, to love, to wonder. But always remember, there is more, much more, worlds within worlds, frequencies you will never hear, colors you will never see, dimensions you will never know. And in that hidden depth, perhaps, lies the truest beauty of all, that the universe is too vast, too mysterious, to be contained in any one experience. You walk through a filtered dream, but the dream is sacred, and the truth, like light beyond the visible, is always there, waiting. Microbes rule you. You think of yourself as one being, one self, one body. But this is an illusion, a convenient story your mind tells to keep things simple. The truth is more complex, more humbling, and more bizarre than most are ready to admit, because you are not one organism. You are a community, a walking, breathing, thinking ecosystem. And most of what makes you was never human to begin with. Inside your body, and especially inside your gut, live trillions of microscopic organisms. Bacteria, fungi, viruses, archaea. They line your skin, coat your mouth, colonize your intestines, and even influence your brain. In fact, microbial cells may outnumber your human cells. Some say by 10 to 1. Others estimate it closer to 1 to 1. Either way, the point stands, you are as much microbe as human, a composite being, a host of hidden passengers. These tiny organisms are not invaders. They are your partners, your co-evolutionaries. Without them, you couldn't survive. They digest the food your body cannot. They synthesize vitamins. They train your immune system. They keep dangerous pathogens at bay. When you take antibiotics, you don't just kill infections, you napalm your inner forest. And when that forest is damaged, strange things begin to happen. Your microbiome, the unique blend of microbes that inhabit your body, shapes far more than digestion. It influences inflammation, metabolism, hormone regulation. It plays a role in obesity, diabetes, autoimmune disease. But perhaps most surprising of all, it may even influence your mind. Emerging research suggests that gut bacteria communicate with the brain through a network known as the gut-brain axis. They send chemical signals through the bloodstream. They trigger the vagus nerve. They modulate neurotransmitters like serotonin and dopamine. In fact, most of the body's serotonin is produced not in the brain, but in the gut. Some researchers now call the gut the second brain. But that may be a misnomer, because it's not just a second brain, it's a shared one. Studies have linked certain microbial profiles to anxiety, depression, and even autism. Mice raised in sterile environments without any microbes display altered stress responses and social behaviors. And when researchers transplant gut bacteria from anxious mice into calm ones, the calm mice begin to show anxiety-like behaviors. The The reverse is also true. Mood may be transmissible by bacteria. Think about that. Your thoughts, your emotions, your cravings, your preferences, all potentially nudged by microscopic beings you cannot see and never consciously control. The desire for sugar, the fog of fatigue, the lift of joy, it may not all be coming from you. Your microbes may have preferences of their own, and they know how to whisper. The foods you eat feed not just your body, but your microbiome. A diet rich in fiber, fermented foods, and plant diversity tends to support a thriving microbial community. A diet heavy in processed sugar, artificial additives, and antibiotics does the opposite. Your microbes adapt quickly. Change what you eat for a week, and your internal ecosystem begins to shift. Some species bloom, others vanish, some may never return. And so the question becomes, who is feeding who? Are you choosing your meals? Or are your microbes nudging you toward the foods that help them thrive? When you crave junk food, is it your will or theirs? This might sound unsettling, but it's also empowering. Because while your microbiome shapes you, you also shape it. The choices you make, what you eat, how you sleep, the stress you carry, ripple through your internal ecosystem. Every bite is a signal. Every night of rest is a message. You are not a prisoner of your microbes. You are their environment, their weather, their world. And just like ecosystems on Earth, your inner world thrives on diversity. A rich microbiome is a resilient one. Modern life tends to strip that diversity away. We live in sanitized spaces, eat monocultured diets, and rely heavily on chemicals. We wash, scrub, and disinfect. In many ways, this is good. It protects us from infection. But in other ways, it starves our microbial allies. We need microbes. We evolved with them. And in the absence of that invisible conversation, systems begin to break down. The rise in allergies, asthma, autoimmune diseases. Some scientists suspect it's tied to a microbial drought. The hygiene hypothesis suggests that our immune systems, deprived of early microbial training, begin to attack the self. Children raised on farms or around animals tend to have lower rates of immune disorders, not because dirt is magic, but because microbes are teachers. And it's not just health. Your identity, the stable sense of self you carry, may also be shaped by microbes. When we talk about the self, we imagine a soul, a personality, a consciousness. But what if part of that is microbial? Your sense of well-being, your energy, your clarity of thought are all intertwined with chemical signals. And many of those signals are produced by the trillions of microbes who call you home. In some cultures, this was intuitively understood. Ancient medical systems like Ayurveda and traditional Chinese medicine have long emphasized the gut, digestion, and balance. Modern science is only beginning to catch up. The concept of you is being rewritten. You are not an island. You are an ecosystem, a rainforest, a reef, a swarm of minds inside a larger mind. And with this shift in understanding comes a shift in responsibility. You are the steward of a vast and invisible world. The foods you choose, the stress you carry, the sleep you protect, these are not just for you. They are signals to your microbes. And in return, they shape how you feel, how you think, even how you age. The microbiome may also play a role in longevity. Some centenarians have been found to possess unusually robust microbial profiles, not just in diversity, but in the presence of species that help suppress inflammation, protect the gut lining, and regulate immune function. Aging is often seen as wear and tear. But what if it's also microbial drift? What if health span depends not just on genes, but on the microbes we carry? Fecal transplants, yes, the transfer of microbiota from one person's gut to another's, have already shown promise in treating infections like C. difficile, and are being studied for broader effects. The future may hold custom-designed microbiomes, precision diets, microbial therapies that reshape mental health, boost cognition, or slow aging. We may soon treat depression not just with pills, but with bacteria. But for now, the lesson is ancient. What lives within you matters. You are not alone. You never have been. And the more we learn, the more we see that life is not a solo act. It is symbiosis, collaboration, a chorus of tiny voices working together to create something larger, something more. So the next time you look in the mirror, remember the face you see is human. But behind the eyes, beneath the skin, flows a river of microbes, countless, ancient, and indispensable. They don't just live inside you, they are part of you. They help define what it means to be alive. And maybe, just maybe, the self isn't a single thing at all, but a harmony. Chaos theory. The butterfly that reshapes the world. You drop a pebble into a still pond, and it sends ripples outward, perfect circles widening into the distance. It feels so orderly, so predictable, so calm. And yet, if you followed each ripple to its edge, traced how it subtly shifted water molecules, insects, the wind that touches the trees above, you might begin to sense something deeper, something stranger. That even in stillness, chaos waits, hidden, sensitive, ready to spiral. This is the heart of chaos theory. The idea that tiny causes can lead to massive, unpredictable effects. That in the dance of nature, small changes can shape everything. At the center of chaos theory lies a haunting truth. Some systems are deterministic, meaning they follow strict laws, but they are still unpredictable. Not because the laws are broken, but because the slightest nudge, the faintest breath of difference in starting conditions, causes them to diverge in wild and uncontrollable ways. This isn't just a philosophical idea, it's a mathematical reality, and it changes how we understand weather, the brain, economies, ecosystems, and even life itself. The idea began with a mathematician and meteorologist named Edward Lorenz. One day he tried to repeat a previous simulation, but instead of entering the initial conditions in full, he rounded them, entering 0.506 instead of 0.506127. It seemed like nothing, insignificant. But the result was dramatically different. The weather patterns evolved in a completely new way. From that tiny change, almost too small to notice, the entire system spiraled into a different future. Lorenz called this the butterfly effect, the poetic idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. This doesn't mean the butterfly causes the tornado. It means that in a system as complex and interconnected as weather, the initial state matters exponentially. And because we can never measure initial conditions with infinite precision, long-term prediction becomes fundamentally impossible. The system is lawful, but unknowable. Predictable in theory, but not in practice. This is the paradox at the heart of chaos. And chaos is everywhere. In the orbits of planets, in the population dynamics of animals, in heart rhythms and brain waves, in the rise and fall of civilizations. It's not disorder. It's not randomness. It's sensitive dependence on initial conditions. It means the world is shaped not just by forces, but by timing, by context, by the smallest of differences. Think of a double pendulum, one arm swinging from another. At first, it moves like you'd expect. Then suddenly it twitches, twists, spirals into chaotic motion. Do it again with the same push, and it moves differently. Do it again, and again, and again. It never repeats. Each time the path diverges, not because the laws change, but because the tiniest variations grow rapidly. That's chaos. Or think of your own life. A missed bus, a delayed flight, a conversation that almost didn't happen. How many major events in your life were shaped by moments that seemed small at the time? That one email, that random meeting, that split-second decision to turn left instead of right. In a chaotic world, these moments are not just chance, they are seeds. Their impact may be hidden at first, but over time they unfold into entire branches of the future. This doesn't mean life is without structure. In fact, chaos has a strange kind of order. When you map the behavior of a chaotic system over time, like the weather or a dripping faucet, you often find patterns, repeating structures, fractals, self-similarity. The system never settles into a stable loop, but it also doesn't wander aimlessly. It dances within bounds, never repeating, never random, always confined to a strange attractor, a region of phase space where chaos lives. The Mandelbrot set is one of the most famous mathematical fractals. Zoom in, and you find spirals within spirals, patterns within patterns, infinite complexity from a simple equation. This is the signature of chaos. That complexity can arise from simplicity. That intricate, beautiful behavior can emerge from a single formula. And it means the boundary between order and disorder is not sharp. It is porous, alive, and endlessly fascinating. Chaos theory has practical implications. It tells us why long-term weather forecasts break down, why economies boom and crash in cycles we can't foresee, why heart rhythms sometimes shift into dangerous patterns, why ecosystems collapse after seemingly small disruptions. It reminds us that stability is often fragile, and that complexity brings vulnerability. But it also brings possibility. Because if small things can lead to big changes, then small choices matter. A single act of kindness, a moment of insight, a shift in mindset, these can ripple outward in ways we can't imagine. In a linear world, change is slow, incremental. In a chaotic world, change can be exponential. You are not just drifting on a current. You are part of a sensitive system capable of shaping futures. Chaos theory challenges our craving for control. We want to believe we can predict that with enough data, enough modeling, we can master the system. But chaos says no. Some systems are fundamentally unpredictable, not because they're broken, but because they are too rich, too intricate, too sensitive. And in that unpredictability, there is humility. The understanding that we don't grasp as much as we think, that the universe is not a clock, it is a storm. And yet, out of that storm, we can still find meaning. Chaos doesn't negate purpose, it deepens it. It means that every moment is ripe with possibility, that the future is not fixed, that the path you walk is not preordained, but co-created by choice, by chance, by context, and that your smallest actions may echo further than you'll ever know. The butterfly effect is not just a metaphor, it's a lens, a way of seeing the world not as static but as alive, pulsing with complexity, breathing with sensitivity, a universe where the present is not a pause, but a pivot, where what seems like a whisper may become a wave. And as you reflect on your life, your choices, your path, consider how much has turned on the tiniest of hinges, the chance encounter, the brief delay, the forgotten word. Chaos reminds us to pay attention, to listen, to move with intention, even when outcomes are uncertain, because in a sensitive world, every step matters. So let the ripple spread, let the butterfly flap its wings, let the unknown remain sacred, and know that within the dance of chaos, there is still beauty, still rhythm, still hope, not because we control it, but because we are part of it. Now is an illusion, the block universe. You sit here listening to these words in what feels like the present, a moment called now. You remember the past, where you were yesterday, who you used to be. You imagine the future, what you might do tomorrow, where you hope to go, and you believe, perhaps without even questioning it, that this moment, this now, is something real, something objective, something moving forward through time. But what if it isn't? What if now doesn't really exist at all? According to one of the most fascinating and unsettling implications of modern physics, the flow of time may be nothing more than an illusion. It's called the block universe theory, a direct consequence of Einstein's theory of relativity, and it suggests that all of time, past, present, and future, exists at once, forever. Not unfolding moment by moment, but laid out all at once in a four-dimensional structure, a cosmic block, a frozen landscape of moments. In this view, time is like space. Just as the entire landscape of a country exists whether you're standing in one city or another, so too does all of time exist, whether you're experiencing 1998, 2025, or the final moments of Earth a billion years from now. You are simply moving through this landscape, and that feeling of motion, that sensation that time is flowing, that's not a feature of the universe. That's a feature of you. Let's begin with relativity. In Newton's universe, time ticked along uniformly, like a great invisible clock in the sky. Every second passed the same for everyone, everywhere. But Einstein showed that this wasn't true. Time is not absolute. It is relative. It moves differently depending on how fast you're traveling or how close you are to a massive object. Clocks tick slower at the base of a mountain than they do at the peak. Time passes differently for astronauts in orbit than it does for people on Earth. Time stretches, warps, bends. And more than that, it mixes with space. Together, space and time form a single fabric, space-time. You can't fully separate one from the other. Events in the universe happen at coordinates in both space and time. But here's the strange part. Depending on your frame of reference, your now might be someone else's then. Two observers moving relative to each other will disagree on whether two distant events happened at the same time. This is called the relativity of simultaneity, and it shatters the idea of a universal present. Think about that for a moment. There is no single, cosmic now that everyone agrees on. What's present for you might already be in the past or still in the future for someone else. Time is not a river that flows for all things equally. It is a landscape, and your experience of it depends on your position, your motion, your perspective. And if there's no privileged now, no objective present moment, then why assume that only the present is real? This leads to the idea of the block universe, that the entire timeline of the cosmos, from the first spark of the Big Bang to the distant heat death of all things, is equally real, that the past hasn't disappeared, that the future isn't waiting to be born, that every moment simply is, eternally, unchangingly, just as all the places on a map exist, even if you're not standing in them. In this model, your birth still exists. Your death already exists. Every moment you've ever lived, or will ever live, exists as a fixed coordinate in the block. You are like a traveler on a train, looking through a window at a passing countryside. The scenery moves, but only from your point of view. The countryside itself never changes. It was always there. The motion is yours, not the world's. So what then is the present moment? That feeling of now, that vivid spotlight that seems to shine on this one sliver of time and not the rest. According to the block universe theory, now is not a property of time, it is a feature of consciousness. Your brain creates the experience of time flowing, of a present moving forward. It strings together moments like frames in a movie, giving you the illusion of motion. But all the frames already exist. You're not really moving. You're just becoming aware of different moments in sequence. It's a humbling idea, a disorienting one, and yet it fits with what we see in the equations. Physics treats time as a dimension. It doesn't distinguish between past and future. The fundamental laws are time symmetric. They work the same forwards and backwards. There's no built-in arrow, no intrinsic flow. Only entropy, the tendency of systems to move from order to disorder, gives us a sense of direction. And even that may be rooted in perspective, not absolute truth. So what does this mean for your life? If every moment exists eternally, does that rob life of meaning? Or does it give you something more profound? Consider this: if all moments are real, if nothing is truly lost, then the people you loved, the moments you cherished, the chapters that seemed to pass too quickly, they're still there. They didn't vanish. They didn't dissolve. They are part of the structure of reality itself, fixed, eternal, preserved. Your first kiss, the sound of your mother's voice, the day you held your child, these are not just memories. They are locations in space and time. You left them behind, but they still are. Just not here, not now, but somewhere. And if this is true, then perhaps there is a kind of quiet comfort to be found, that your story is not a flame that flickers and dies, but a constellation of moments, each one eternally glowing in the fabric of existence. You are not just a traveler moving from past to future. You are a being stretched across time, a body in 4 dimensions, a timeline, not just a point. This view also raises questions about fate and free will. If the future already exists, does that mean it's fixed? That every choice is predetermined? That you're just playing out a script? Perhaps, or perhaps not. The block universe doesn't say whether the future was written by rules or randomness, only that it's there. But how it got written may still be up for debate. And what of death? In the block universe, death is not the end. It is simply another moment, another coordinate. You do not cease to exist. You simply no longer exist here, just as you no longer exist at your birth. But your birth still exists. You are not erased. You are eternalized. Your entire life, a sculpture in time. It's a strange kind of immortality, not the kind we imagine, not endless consciousness or golden afterlives, but the immortality of structure, of being woven into the fabric of the cosmos forever. Your smile, your tears, your presence, carved into time like fossils in stone. And so, the block universe invites a different kind of mindfulness, a reverence for the moment, not because it is fleeting, but because it is forever. Every breath you take, every word you speak, becomes part of the tapestry. You are writing not on sand, but on the walls of reality. And maybe, just maybe, this also reshapes how we see each other. Because if every person is a timeline, then every life is a world. Every mind a stretch of moments. Every interaction a crossing of paths. The people you love, the people you hurt, the people you pass by. Each one is living a story just as real, just as permanent as your own. We often talk about living in the now, but perhaps that phrase means something deeper than we thought. Not just seizing the moment, but honoring its place in eternity. Understanding that this moment, yes, this one is real forever. It will never unexist. It is a part of the universe's memory. It is carved into the block. And so we return to where we began, sitting here, listening, breathing, in what feels like the present, but knowing now that this present is a perspective, not a place. That what we call now is not a universal spotlight, but a candle flickering through an eternal cathedral. That behind the veil of motion lies a stillness deeper than time. That every moment is always somewhere. And that you, wherever and whenever you are part of that great and silent block, forever.